welcome to another deep dive.
All right.
Today, we're
Okay.
we're going to be talking about fluid dynamics.
Okay.
But hold on tight, because this one is going to get pretty mathematical.
Sounds good.
You, our expert listener, are going to love this.
I'm ready. All right.
Let's do it.
We are tackling a research paper titled Existence, Uniqueness, and Asymptotic Stability of Invariant Measures for the Stochastic Allen-Cahn-Navier-Stokes System with Singular Potential.
Wow.
It sounds intimidating, but trust me, it's fascinating stuff.
It is. It's all about understanding how fluids mix, but on a very deep mathematical level.
Okay. So imagine oil and water.
Right.
They don't fully blend, right?
Yep.
They create that distinct interface. This paper uses a model called the Allen-Cahn-Navier-Stokes equation to describe this kind of mixing. And they've even added random elements.
Making it stochastic to capture the unpredictable nature of real-world fluids.
Oh, like trying to predict the exact patterns that form when you shake a bottle of salad dressing?
Exactly.
There's a lot of randomness involved.
Yeah. And to make sense of that long-term behavior, even with all that randomness, we need a special tool, right?
We do?
We need invariant measures.
Right.
So these measures help us find the stable states that a system settles into over time. Sort of like finding the mathematical equivalent of a pendulum finally coming to rest.
They're a way to see the forest for the trees, focusing on the overall trends rather than those tiny random fluctuations.
Okay, so let's unpack the real-world problem that this paper tackles.
Right.
They're focused on how two immiscible fluids, like our oil and water example, mix or partially mix. They use a diffuse interface approach, meaning they model the transition between the fluids as a continuous gradient rather than a sharp boundary.
It's like imagining a blurry zone where the oil and water gradually blend into each other rather than a hard line separating them.
And understanding this mixing behavior is incredibly important for fields like biology, materials, science, and even radiotherapy.
Absolutely. For instance, similar models are used to study liquid phase separation in cells, which has implications for radiation therapy research, especially in an exciting area called FLAsh radiotherapy. That's changing how we approach cancer treatment.
So this seemingly abstract mathematical model has the potential to impact how we treat diseases.
Exactly. It highlights how fundamental mathematics can have tangible real-world applications.
Absolutely. Now, let's get into the heart of the mathematical model itself. It all starts with something called an order parameter, represented by the Greek letter.
Yes.
This acts as a label for each fluid. If equals 1, it's one fluid. If equals -1, it's the other.
And the values in between -1 and 1, represent that diffuse interface where the mixing occurs.
But there's a catch, right?
There is.
Can't just be any random number.
Right.
It has to stay within that -1 to 1 range to make physical sense.
The model needs to be physically consistent.
Right.
We can't have more of a fluid than physically exists.
Right.
So needs to stay within those bounds. Yeah.
That makes sense. Now, they also mention a logarithmic potential.
Yes.
Can you explain what that is?
So the logarithmic potential is a mathematical function that captures the energy associated with mixing. Think of it as a way to quantify the forces at play within that diffuse interface.
So it tells us how much effort it takes.
In a way, yes. It's a measure of the energetic cost of creating and maintaining that interface between the fluids.
Okay, we've got our order parameter and this energy function. But how does the model actually capture?
Right. So that's where two powerful equations come into play. The Cahn-Hilliard equation and the Allen-Cahn equation. They describe how evolves as the fluids mix.
So they give us a mathematical movie of the mixing process.
Precisely.
Showing how that interface shifts and changes.
Exactly. But the model goes even further to incorporate fluid flow. They couple the Cahn-Hilliard or Allen-Cahn equation with the famous Navier-Stokes equations.
Ah, Navier-Stokes?
Yeah.
Those describe how fluids move,
yeah,
right?
Exactly. They govern fluid flow.
Okay.
Taking into account factors like viscosity and pressure.
Okay.
And to link these equations with the Cahn-Hilliard or Allen-Cahn equation, they introduce the Korteweg force, which models the effects of surface tension.
Okay.
You know, that tendency for fluids to minimize their surface area.
So they're creating an even more realistic model.
Right.
By capturing those subtle forces that shape how fluids behave.
Exactly.
And remember how we talked about the model being stochastic?
Right.
Yes. So to capture the randomness of real-world mixing, they add noise terms at the equations, driven by what are called Wiener processes. It's like introducing tiny, unpredictable jiggles into the system, acknowledging that we can't perfectly predict how every single molecule will behave.
And that brings us to the heart of the model. The stochastic Allen-Cahn-Navier-Stokes equation, labeled as equation 1.2 in the paper.
Okay. It looks pretty intimidating, right?
It does.
With terms for the velocity field, pressure, those noise terms, G1 and G2, parameters for viscosity and interface thickness, and so much more.
So much.
It's like a mathematical recipe for fluid mixing chaos.
It is. And they focus specifically on the case with Dirichlet boundary conditions.
Dirichlet boundary conditions?
Yeah.
What do those mean again?
It means that the values of a toy are fixed at the edges of the domain where the mixing is happening.
Okay.
Imagine setting the temperature at the walls of a room.
Okay.
It influences how the heat flows inside.
Right.
Dirichlet boundary conditions are like setting those temperature values at the edges of the container.
So the container's influence on the mixing
Precisely.
is also factored into the model.
This sets the stage for understanding
the core question of the paper.
All right.
What happens to these fluids after they've been mixing for a long time?
Yeah.
Do they settle into a predictable state despite all the randomness?
And that's where those invariant measures come back into play, right?
They do.
They help us find those mathematical resting points
for
the fluid mixture, even with all that stochastic jiggling going on.
The paper uses some heavy-duty mathematical techniques to explore those invariant measures.
Yeah.
The Krylov-Bogoliubov method for proving their existence, and a generalized coupling technique for proving their uniqueness.
Wait, so there could be multiple stable states?
That's what the math suggests.
Wow.
But by proving uniqueness, we can pinpoint the specific configuration that the system will eventually settle into.
Okay. So we're on a quest to find those stable states.
We are.
What can you tell me about these techniques? Krylov-Bogoliubov.
And generalized coupling.
So the Krylov-Bogoliubov method involves averaging the system's behavior over long periods.
Okay.
It's like taking a time-lapse video of the mixing process and analyzing the patterns that emerge, ignoring those tiny random fluctuations and focusing on the overall trends.
Okay. And what about generalized coupling?
Imagine you have two identical bottles of oil and water, but you shake them slightly differently.
Okay.
The coupling technique lets us mathematically link these two systems and observe whether they eventually end up in the same final state, despite those different initial conditions.
So it's a way to test the robustness of those stable states to see if they're truly the inevitable destinations for the system, regardless of how the journey begins.
If all roads really do lead to room, even if we take different routes. Yeah.
That makes sense.
Now, I also noticed the paper mentions something called Foyas-Prodi estimates.
Yes.
What are those all about?
Foyas-Prodi estimates are all about control and prediction.
Okay.
They essentially say that if you can control enough of the key patterns of fluid motion, the low modes, think of them as the most prominent swirls and eddies. And if BPBO, that interface thickness parameter, is large enough, then you can synchronize the long-term behavior of two solutions, even if they start from different.
So it's like saying, if we can tame the most influential aspects of the flow,
precisely,
then we can make the overall mixing process more predictable, regardless of the initial state.
And this links back to the invariant measures.
Okay.
Because if we can control the system enough to make different starting points converge to the same state, it strengthens the idea.
That there's a unique and stable state.
Okay.
That the system is drawn towards.
I see how all the pieces are starting to connect.
They are. They are.
You also mentioned ergodicity earlier.
Right.
What does that mean in the context of all this fluid mixing?
So ergodicity is a powerful concept.
Okay.
Imagine vigorously shaking that bottle of oil and water.
Yeah.
Ergodicity would mean that over a long time, the mixture spends roughly the same amount of time in every possible configuration it can achieve.
So it's like saying there are no forbidden configurations.
Exactly. Okay. And if we tracked the average state of the mixture over a very long time, it would match the average state if we took instantaneous snapshots of a million different bottles that had been shaken for a long time.
So it connects the long-term behavior of a single system to the statistical properties of many similar systems.
It does.
Okay, my brain is definitely getting a workout here.
I bet. I bet.
But before we dive into the paper's main results, is there anything else we need to cover?
Just one more thing.
Okay.
Remember how we said the paper focuses on Dirichlet?
Yes.
Boundary conditions for the order parameter?
Yes, those fixed values at the container's edges.
Right. They get even more specific.
Okay.
Introducing these spaces denoted by as, which essentially categorize the order parameters based on how much energy it takes for them to deviate from their boundary values.
Okay.
They also introduce a, which is a space for those that never quite reach the full one or nadish one values. So there's always some degree of mixing happening.
So it's like they're zooming in on specific types of that have particular energy constraints.
And they use these spaces to define new spaces, XREG and YAREG, which essentially contain the
well-behaved initial conditions.
Well-behaved in the sense that they lead to solutions.
They are the initial conditions that play nicely with the theory and allow us to prove those powerful results about invariant measures.
Okay. So we've set the stage, introduced the key players, and even organized them into neat categories. I'm ready to hear what the paper actually discovered.
Me too.
Let's delve into those key results.
Okay.
So let's get to the heart of the matter, the key results. The paper proves several important things. First, it shows that there's at least one invariant measure for this system.
So even with all that random noise, there's at least one resting point that the fluid mixture could eventually settle into.
Exactly. But here's where things get really interesting. They also prove that under specific conditions, that invariant measure becomes unique.
Oh, so there's only one final destination for the system if certain criteria are met. What kind of criteria are we talking about?
One key factor is the viscosity of the fluids. Remember, viscosity is a measure of how sticky a fluid is. Honey has high viscosity, while water has lower viscosity.
Right, I get it. So the stickier the fluids, the more likely they are to settle into a single stable state.
That's one factor. They also need those Dirichlet boundary conditions we talked about, those fixed values of at the edges of the container.
So the container's influence plays a role in ensuring there's just one stable state. What else?
The intensity of the random noise also matters. And of course, how much control we have over those dominant patterns of fluid motion, the low modes. It's a fascinating interplay between all these factors.
It sounds like a delicate balancing act. The stickiness of the fluids, the randomness they're subjected to, the influence of the container, and our ability to control the major flow patterns. If we get all of that just right, we can guarantee that the mixture will settle into a unique, stable state.
Precisely. And the paper goes even further. They prove that this unique invariant measure is asymptotically stable.
Asymptotically stable. What does that mean exactly?
It means that as time goes on, the system gets closer and closer to that unique, stable state. It's like there's a magnetic pole drawing it in.
So it's not just that the stable state exists, but the system is inevitably drawn towards it over time.
That's right. And this gives us a powerful mathematical framework for predicting the long-term behavior of these complex mixtures, even with all the randomness involved.
This is impressive. It seems like the paper really dives deep into the mathematics of fluid dynamics. But I do have one question.
Go ahead.
I kept seeing references to strong solutions and martingale solutions. Could you clarify the difference between those? I'm a bit fuzzy on the distinction.
You're right, those terms do pop up a lot. The distinction comes down to how we handle the randomness, the stochasticity in the system. Think of them as representing different levels of mathematical certainty.
So strong solutions are the ones where we have the most certainty.
Yes, you could say that. A strong solution to the stochastic Allen-Cahn-Navier-Stokes equation means we have a solution that satisfies all the necessary conditions in a very rigorous path-by-path sense.
Path-by-path meaning?
It means that for every single possible sequence of those random jiggles, every possible realization of the random noise, the solution exists and behaves as expected.
So it's like saying no matter how chaotically we shake that bottle of oil and water, we have a solid mathematical description of what happens.
Exactly. But sometimes proving the existence of such strong solutions can be very challenging. That's where martingale solutions come in.
So they're a bit weaker.
In a sense, yes. Martingale solutions allow for a bit more flexibility. Instead of demanding a solution for every single possible noise realization, they consider solutions in a probabilistic sense. They might allow for different solutions on different parallel universes of randomness as long as certain overall probabilistic properties are satisfied.
So it's like saying, okay, we might not be able to predict exactly what will happen in every single possible scenario, but we can still understand the overall statistical behavior of the mixing processes.
Precisely. It's a powerful tool for dealing with situations where the randomness is so complex that nailing down a single deterministic solution is incredibly difficult.
Okay, that makes a lot more sense now. It's like we're trading some certainty about individual paths for a broader understanding of the probabilities at play.
That's a great way to put it. And often, proving the existence of a martingale solution is a stepping stone towards eventually demonstrating the existence of a unique, strong solution. It's like building a bridge from a broader, probabilistic understanding to a more precise path-by-path description.
Okay, that clarifies things. Back to those key results. The paper proves that under the right conditions, there is a unique, asymptotically stable invariant measure. It's fascinating that we can predict the long-term behavior of these mixtures, despite the inherent randomness of the mixing process.
It is a remarkable result, and it highlights the power of math to reveal order and predictability within systems that might seem chaotic.
It's like saying that even though we can't control every single jiggle of a molecule, we can still understand the large-scale patterns that emerge over time.
Exactly. And this has significant implications for those real-world applications we talked about earlier, like biology, material science, and cancer treatment.
Right. This mathematical framework could lead to better experiments, new materials, and even optimized treatment strategies.
Absolutely. It's a great example of how theoretical math research can have very practical impacts in various fields.
Let's talk a bit more about those Foyas-Prodi estimates. I understand that if we can control enough of those low modes, we can synchronize solutions. But what does it mean to control them? And how do we identify which ones are the low ones?
Great question. The low modes represent those dominant patterns of fluid motion. Think of the large-scale swirls and eddies you see when you stir a cup of coffee. Those are what the low modes capture. They have the most energy and influence over the overall flow.
So they're like the bass notes in a piece of music. They set the foundation and the rhythm for the whole piece.
That's a perfect analogy. Now, controlling those modes means being able to influence their amplitude, how strong those swirls and eddies are. In the paper, they introduce a control term in the Navier-Stokes equation to specifically target these low modes.
So it's like we have these tiny invisible paddles within the fluid that can nudge those dominant patterns in certain ways.
Exactly. But how do we know which ones are the low modes? Well, it involves some pretty advanced math eigenfunction decompositions, projections, but essentially we can break down the complex velocity field into a combination of these simpler fundamental patterns, each with its characteristic frequency and spatial structure.
So it's like taking that complex swirling motion and separating it into a collection of simpler motions.
Precisely. And the Foyas-Prodi estimates tell us that if we can control enough of these low-frequency, large-scale patterns, the ones carrying the most energy, and if it's efficiently large, we can essentially make the system behave more predictably, forcing different solutions to converge over time.
So we're taming the most influential parts of the flow to guide the entire mixing process toward a desired outcome.
Makes sense. You mentioned that, Bob, the interface thickness parameter needs to be large enough. Why is that?
Great question. Remember, Bakke determines how fuzzy that interface zone is between the two fluids. A small BOF means a sharp, well-defined interface. Think of a distinct line between oil and water. But when Bob is large, The interface becomes more diffuse, more spread out. Think of a gradual gradient between the two fluids.
So a more spread out interface makes the mixing easier to control.
It's not necessarily about being easier to control, but it changes the dynamics of the system. A larger off means more interaction and diffusion between the fluids, which, under the right conditions, can make the system more stable and less sensitive to those initial differences that the Foyas-Prodi estimates are all about.
So a thicker interface zone acts as a buffer, smoothing out the initial discrepancies and helping the system settle into a more predictable long-term state.
Exactly. It's a subtle but critical part of the overall picture. I'm feeling much more confident in our understanding of the Foyas-Prodi estimates now. Before we move on, can we peek a little deeper into the mathematical proofs themselves? I know we can't get too technical, but I'm curious about what kinds of mathematical tools they use.
I was hoping you'd ask. One of the key steps in proving the Foyas-Prodi estimates involves subtracting the equations for U and A, which represent the velocity fields of the original system and the controlled system, respectively. This gives us an equation for the difference between them, denoted as U, which we then analyze to see how it evolves over time.
So we're isolating the impact of that control term we added to the Navier-Stokes equation.
Exactly. Here's where it gets interesting. We multiply that difference equation by U itself. This trick allows us to exploit the structure of the Navier-Stokes equation. The convective term U vanishes when we do this multiplication.
Why would it vanish? It seems like it should become even more complicated.
It vanishes because of the nature of the dot product and the fact that the velocity field is divergence-free. Remember how we mentioned that the velocity field U satisfies the condition div U equal 0? This means when we take the dot product of A with the gradient of U, something special happens.
What happened?
Mathematically, UAU is equivalent to 1/2 the divergence of U times the magnitude of U squared. Since div U is 0, the whole term disappears. It's a consequence of the underlying physics, specifically the incompressibility of the fluid.
Wow, that is a neat trick. By taking advantage of that property, we can simplify the equation and focus on the important terms.
Precisely. That's how we can start to tease out those conditions involving if, in, and bia, showing that if the right constraints are in place, that difference term U decays over time, leading to that synchronization we're after.
Okay, I'm starting to see the elegance of these proofs. They're not just brute force calculations, but clever manipulations that exploit the structure and symmetries of the equations.
You've got it. It's like a mathematical dance, where each step is guided by the rhythm of the equations themselves.
You also mentioned integrating up to a stopping time. What's the purpose of that?
Stopping times. They're a powerful tool in stochastic analysis. Remember how martingale solutions allow for solutions in a probabilistic sense? Stopping times give us a way to pause the system's evolution at certain moments, often when specific conditions are met.
So it's like setting a timer that goes off when something noteworthy happens in the mixing process.
That's a good way to think about it. For the Foyas-Prodi estimates, they use a specific stopping time, denoted by 10R, which acts like a safety net to prevent the system from blowing up, becoming unbounded, or behaving erratically.
It's like a circuit breaker that prevents the system from going haywire.
Exactly. By carefully choosing the stopping time and integrating the equations up to that point, they can control the growth of various terms and make sure the estimates remain valid, even when the randomness throws things off track.
Okay, I see how stopping times add another layer of sophistication to these proofs, taming the wildness of the stochasticity and allowing us to draw out insights about synchronization and stability.
Precisely. It's a beautiful interplay between probability, analysis, and the physics of fluid dynamics.
We've covered a lot. Invariant measures, Foyas-Prodi estimates, strong and martingale solutions, and even stopping times. What's next?
Let's talk about how the paper goes about proving the uniqueness of that invariant measure. They use a generalized coupling technique.
Can you remind me what coupling is all about?
Imagine those two bottles of oil and water, again, shaken slightly differently. Coupling is a mathematical way to link those two systems, to correlate their random jiggles in a specific way, and then see if they reach the same final state despite those initial differences.
So it's a way to test if that stable state is really robust.
Precisely. Now, the paper actually uses results from other papers as tools for their mathematical proof. They use a theorem from 45, which provides conditions for the uniqueness of an invariant measure for a Markov chain.
Markov chain. Could you refresh my memory on what that is?
Think of a system that jumps between different states randomly. In our case, the states are the different configurations of the fluid mixture, how the oil and water are distributed. The Markov property just means that the system has no memory beyond the most recent step. The current state only depends on the state right before it, not the entire history.
So we're simplifying the problem by only looking at the most recent snapshot of the mixing process.
Exactly. The theorem from 45 essentially says that if we can find a set of initial conditions where the coupled systems have a positive probability of converging over time, then we can conclude that there's only one invariant measure that lives within that set.
So if some paths lead to the same destination, then there can only be one Rome for the system.
That's the idea. And to prove this convergence, they use those Foyce-Prodi estimates we discussed earlier.
So the Foyce-Prodi estimates help control the system, making those different solutions converge. And that convergence allows us to apply the theorem from 45 to prove uniqueness.
Exactly. It's a beautifully crafted chain of reasoning, building on previous findings, and combining them in a smart way to uncover new insights.
And what about that other paper, 56? What role does that play?
56 provides a powerful result about asymptotic stability. It essentially states that if we can show that for almost all initial conditions, the solutions to the coupled systems converge in probability, meaning that the chance of them being far apart becomes increasingly small over time, then the invariant measure is not only unique, but also attracts all those solutions.
So it's like the gravitational pull of that unique stable state becomes irresistible for almost any starting point.
That's a great way to put it. Again, they use those powerful Foyce-Prodi estimates to establish this convergence in probability, showing how versatile those estimates are.
Those Foyce-Prodi estimates really are the foundation of this paper. They're not just a side note, but the key to unlocking several major results.
You're absolutely right. It's worth pointing out that these techniques, coupling, and Foyce-Prodi estimates are not limited to this particular fluid dynamics problem. They're used in various fields, from chemical reactions and climate models to financial markets.
It's amazing how these abstract mathematical tools can be applied to such diverse areas.
It really highlights the power and universality of math.
Okay, let's dive into the specifics of how they use this generalized coupling technique. What does the setup look like?
Get ready for the details. They start by choosing a specific set of initial conditions. X, Y arrows, remember those spaces we talked about that categorize the order parameters based on their energy constraints?
Yes. Y's is the one related to the logarithmic potential.
That's the one. For every pair of initial conditions within this set, denoted as X, Y, and S, they introduce two coupled systems. The first is the original stochastic Allen-Cahn-Navier-Stokes system, starting from X.
That's our control system, the one we're comparing everything to, right?
Yeah, exactly. The second system is a slightly modified version of the original, starting from X. The key difference is that we add a control term to the Navier-Stokes equation. Remember those invisible paddles we discussed earlier?
Yes. So we're nudging the second system in a very specific way, targeting those dominant patterns of fluid motion.
Precisely. The goal is to show that with the right conditions, we can choose this control term so that the solutions to the two systems denoted as U for the original and for the modified system converge over time.
We're using those invisible paddles to steer the second system toward the same long-term state as the first system, even if they start on different paths.
Exactly. To ensure this convergence, they introduce some extra conditions. They require that the dimension of the space where we apply the number of low modes we're targeting is large enough.
We need enough paddles to effectively guide the flow.
Right. They also require the interface thickness parameter to be sufficiently large.
Yes, that buffer zone that helps smooth things out.
Exactly. They also introduce a key concept, a stopping time denoted by 10R. This stopping time acts as a safety measure.
A safety measure. How so?
Remember that in martingale solutions, we allow for solutions in a probabilistic sense, which means there could be unpredictable paths where things go off the rails. This stopping time helps control that. It pauses the system's evolution if certain quantities become too large, for example, if the system's energy starts to grow uncontrollably.
So it's like a pressure valve that prevents the system from exploding by releasing excess energy.
That's a great analogy. By strategically choosing the stopping time and analyzing the solutions up to that point, they can derive some important estimates that guarantee convergence.
It's like we're setting limits on how unpredictable the system can be. And within those limits, we can prove that convergence happens with a certain probability.
Exactly. These estimates involve a complex interplay between viscosity, interface thickness, and the intensity of the random noise. It's a beautiful example of how we can combine probabilistic and analytical techniques to understand stochastic systems.
This is getting pretty complex. What kind of math are they using for those estimates?
They use a whole toolkit of advanced mathematical techniques: Grunwald's inequality, the Burkholder-Davis-Gundy inequality, Sobolev embeddings, and more. Each tool plays a specific role in taming different aspects of the problem.
It's no wonder this paper is aimed at a math-savvy audience.
It's a symphony of high-level math. Proving those estimates is challenging, involving pages of intricate calculations and clever manipulations.
I can imagine. But the payoff is huge. We gain a deep understanding of how those coupled systems evolve and converge over time.
Precisely. And that convergence is the key that allows them to use those powerful theorems from 45 and 56 to establish the uniqueness and asymptotic stability of the invariant measure.
Let me make sure I understand this coupling approach. We set up two systems, a control system and a modified system with a control term. We choose a specific stopping time to prevent things from spiraling out of control, and we derive crucial estimates using some advanced mathematical inequalities. Then, we use those estimates and the convergence they guarantee to apply those theorems and prove uniqueness and stability. Did I get that right?
You nailed it. It's a testament to the ingenuity of mathematical reasoning.
Okay, my brain is definitely full. But I have one final question before we move on.
Fire away.
The paper focuses on Dirichlet boundary conditions for the order parameter, those fixed values at the container edges. Why is that choice so important? What would happen if they chose different boundary conditions?
That's a sharp question. The choice of boundary conditions is crucial in this analysis. Remember, boundary conditions determine how the system interacts with its surroundings, in this case, the walls of the container.
Right. They're like the rules governing how the fluids behave at the boundaries.
Exactly. And the specific boundary conditions we choose can drastically affect the system's long-term behavior, influencing whether invariant measures exist and whether they are unique.
So could different boundary conditions lead to different stable states?
Absolutely. Dirichlet boundary conditions, those fixed values at the edges, act like constraints, forcing the order parameter to behave in certain ways near the boundaries. This can make the system more stable and more likely to settle into a single stable state.
It's like those fixed boundaries create a stabilizing effect, helping to tame the randomness of the mixing.
That's a good way to think about it. But with different boundary conditions, like Newman boundary conditions, where the derivative of pool is fixed at the boundaries, the behavior could be completely different. The system might have more freedom to fluctuate near the edges, leading to multiple stable states or preventing it from settling down at all.
So the choice of boundary conditions isn't just a technical detail. It can fundamentally change how the system behaves.
Exactly. Exploring different boundary conditions is an ongoing area of research in fluid dynamics. It's like adjusting the rules of the game and seeing how the players, in this case, the fluids, change their strategies.
It really makes you wonder what would happen if they changed those fixed values at the boundaries. Could we see completely different mixing patterns if they, tweaked those fixed boundary values?
Absolutely. Imagine swapping Dirichlet boundary conditions for Newman boundary conditions.
Okay.
Instead of fixing the values of S at the edges, we would fix the rate of change of S.
Okay.
It would be like saying, instead of dictating the exact temperature at the walls, we're controlling how quickly the temperature changes near the walls.
So we're giving the fluids a bit more freedom at the boundaries. How would that affect things?
It could make the system much more sensitive to the initial conditions.
Yeah.
Remember, the Foyers-Prodi estimates rely on controlling those dominant flow patterns to make different starting points converge.
Right.
But with Newman boundary conditions, those edges could become areas of unpredictable behavior, making it harder to guarantee a single stable state.
So instead of settling into one realm, the mixture might be pulled towards multiple destinations.
Or it might never settle down at all,
right,
constantly fluctuating near the boundaries.
Wow.
It highlights how even seemingly technical details like boundary conditions can have a huge impact on the system's overall behavior.
It's amazing how much complexity is packed into these simple mixing scenarios.
It is. And it underscores the power of mathematics to analyze these complexities and find order and predictability within what might appear to be chaos.
It seems like we've thoroughly explored this paper.
We have.
Before we wrap up, can we dig into some of the specific mathematical details of the proofs?
Absolutely.
I'm particularly interested in those Foyers-Prodi estimates.
The Foyers-Prodi estimates are a cornerstone of this paper. And the proofs involve some elegant mathematical maneuvering. Do you want to start with how they establish the difference equation for the controlled and uncontrolled systems?
Yes, let's start there. How do they isolate the effects of the control term?
They begin by taking the difference between the equations for the velocity fields of the original system, denoted by U, and the controlled system, denoted by E. This gives them an equation for the difference. U equals U minus E. Then they analyze how this difference U evolves over time.
That makes sense. By looking at the difference, they're essentially isolating the impact of that control term.
And here's where things get really clever. They multiply that difference equation by U itself. This allows them to leverage the unique structure of the Navier-Stokes equation.
What's so special about multiplying by U?
Well, a remarkable thing happens when you do that. The convective term in the Navier-Stokes equation, UU, disappears.
That sounds counterintuitive. Why would multiplying by U make that term vanish?
It all comes down to the properties of the dot product and the fact that the velocity field is divergence-free. Remember, the velocity field satisfies the condition div U equals 0. This means that when you take the dot product of with the gradient of U and then dot that with U again, something interesting happens.
I'm following it so far. What's the interesting thing that happens?
Mathematically, your UU is equivalent to 1/2 the divergence of U times the magnitude of U squared. But since div U is 0, the entire term becomes 0. It's a direct consequence of the fluid's incompressibility.
Wow, that's a neat trick. So by exploiting that property, they can simplify the equation and focus on the terms that really matter.
Exactly. That's how they start to derive those conditions involving UMN and body, showing that if the right constraints are in place, that difference term, decays over time, leading to the synchronization they're looking for.
This is really making me appreciate the elegance of these mathematical proofs.
It is elegant.
It's not just about brute force calculation. It's about understanding the structure of the equations. And using clever manipulations to extract meaningful insights.
You're absolutely right. It's like a delicate dance where each step is guided by the inherent harmony within the equations.
Now, you mentioned integrating up to a stopping time. Do you explain why they do that?
Stopping times are a powerful tool in stochastic analysis. They provide a way to pause the system's evolution at strategic moments, often when certain conditions are met. Remember how we discussed that martingale solutions allow for solutions in a probabilistic sense? Well, stopping times allow us to manage the unpredictability inherent in those solutions.
So it's like setting a safety limit.
That's good analogy.
A point where we say, okay, things are getting too wild here. Let's pause and reassess this.
In the context of the Foyer's-Prodi estimates, they introduce a specific stopping time, denoted by 10A, which acts like a safety net, preventing the system from blowing up, becoming unbounded, or exhibiting erratic behavior.
So it's like a pressure release valve that prevents the system from exceeding certain bounds.
Precisely. By carefully choosing this stopping time and integrating the equations up to that point, they can control the growth of various terms and ensure that those estimates remain valid even when the random fluctuations try to throw things off course.
That's fascinating. It's like they're imposing order on the chaos, using these mathematical tools to tame the randomness and extract meaningful insights.
Exactly. It's a testament to the power of combining probabilistic and analytical techniques to unravel the complexities of stochastic systems.
Okay, so we've delved into the depths of the Foyer's-Prodi estimates. What other mathematical gems are hidden within this paper?
Well, the paper uses a whole array of sophisticated techniques to derive its results. For instance, when proving the uniqueness of the invariant measure using the generalized coupling technique, they rely on some heavy-hitting inequalities, like Gronwall's inequality and the Burkholder-Davis-Gundy inequality.
I've heard of Gronwall's inequality, but I'm not familiar with the Burkholder-Davis-Gundy inequality. What's that one all about?
The Burkholder-Davis-Gundy inequality is a powerful tool for estimating the maximum value of a stochastic process. It essentially relates the maximum of a martingale. Remember, a martingale is a type of stochastic process with certain special properties to its quadratic variation.
Quadratic variation. That sounds a bit intimidating. Can you break it down for me?
Quadratic variation is a measure of how much a process fluctuates over time.
Okay.
It's a way to quantify the wiggliness of a stochastic path.
So a process with high quadratic variation is one that jumps around a lot.
Exactly. And the Burkholder-Davis-Gundy inequality tells us that we can bound the maximum value of a martingale by a function of its quadratic variation.
Okay.
This is incredibly useful because it allows us to control the extreme values of a stochastic process, even when the process itself is driven by random noise.
Okay, I'm starting to see how that could be useful in the context of the fluid mixing problem.
Yeah.
But how does it specifically tie into the proof of uniqueness?
Well, remember how we discussed that the generalized coupling technique involves comparing the solutions of two coupled systems? The Burkholder-Davis-Gundy inequality comes into play when they're analyzing the difference between those solutions.
So they're using it to estimate how far apart those solutions can get over time, even with all that random noise influencing the mixing.
Precisely. By controlling the maximum difference between the solutions, they can demonstrate that the probability of those solutions diverging becomes arbitrarily small over time. This ultimately leads to the conclusion that there can be only one invariant measure that all paths eventually lead to.
That's amazing. It's like they're using this inequality to impose a kind of closeness constraint on the coupled systems, forcing them to stay within a certain probabilistic distance of each other as they evolve.
You've got it. It's a brilliant example of how mathematicians can harness the power of abstract inequalities to derive deep insights into the behavior of complex systems.
It really is a testament to the elegance and ingenuity of mathematical reasoning.
It is.
Okay, I think my brain is officially overflowing with mathematical insights for today.
As is mine.
I think we've thoroughly explored the depths of this paper.
Let's have.
It's been a fascinating journey.
It has been.
Through the intricacies of fluid dynamics, stochastic analysis, and advanced mathematical techniques.
Absolutely.
It's amazing how these seemingly abstract concepts can have such profound implications for understanding real-world phenomena.
Exactly. This paper is a prime example of how theoretical research can lay the foundation for practical advancements in various fields, from medicine to material science.
Well, thank you for guiding me through this incredible deep dive. It's been an intellectually stimulating and rewarding experience.
It's been my pleasure. And to our listeners, thank you for joining us on this mathematical adventure. We'll see you on the next deep dive.
All right, so today we're going to be taking a look at a paper called Existence, Uniqueness, and Asymptotic Stability of Invariant Measures for the Stochastic Allen-Cahn-Navier-Stokes System with Singular Potential.
Wow, that's a mouthful.
It is. It is. But, you know, it's fluids. It's stochastic equations. And some pretty heavy theorems. You ready for this?
Absolutely. This paper is really diving deep into a really fascinating area, how to model the long-term behavior of fluids that don't mix, like fully mix, even when you take into account all the randomness of the real world.
Yeah, and they use this diffuse interface approach, which is like smoothing out the boundaries between the fluids. So that the math is a little bit easier to work with.
It is. Imagine trying to model the exact boundary between like oil and water in a turbulent flow. It would just be a nightmare. So the diffuse interface approach basically says, okay, let's simplify this. Let's allow for a little bit of mixing in a thin transition zone.
And that way we can use these powerful mathematical tools like partial differential equations to analyze the system.
So instead of like a hard line, it's more like a gradient.
Exactly.
And then on top of that, they're adding stochasticity into the mix, which accounts for all those real-world factors that you just can't predict.
Absolutely. And that's what I think is so interesting about this work, They're not shying away from the complexity. They're using these things called stochastic partial differential equations to model those random influences. Think about like tiny temperature fluctuations or impurities in the fluids. It adds a whole other level of complexity to the problem.
It's like trying to predict the weather, where there's all these tiny little unpredictable factors that can have a huge impact on the outcome.
That's a perfect analogy.
Right.
And so just like predicting the weather, understanding the long-term behavior of these complex fluids is a huge challenge.
Right. That's where this concept of invariant measures comes in.
Okay.
Think of them as like statistical snapshots of the system's long-term behavior.
Correct.
A way to see through the randomness and get a sense of where the system is headed.
So these invariant measures, they're like a crystal ball, helping us predict the future of these like crazy fluids.
You got it. And this whole paper is all about proving the existence, the uniqueness, and the stability of these invariant measures for this specific model known as the stochastic Allen-Cahn-Navier-Stokes system.
Right. And this equation it's got a lot of power to it.
It does.
Because it combines the Navier-Stokes equations, which describe fluid flow, with the Allen-Cahn equation, which models phase separation.
Precisely. So you've got the Navier-Stokes part handling the motion of the fluid.
Right.
And then you've got the Allen-Cahn part that's dealing with how the different components of the fluid want to separate from each other.
Okay.
Like, think about oil and water trying to disentangle themselves.
Right.
That's what the Allen-Cahn equation is capturing.
So this equation is like a dynamic recipe.
Yes.
It combines those rules of fluid flow with the rules of separation.
Exactly.
To give us this comprehensive picture of how these complex systems actually change over time.
You got it. And this paper goes on and proves some remarkable things about the long-term behavior of this system. They actually show that under the right conditions, there is one and only one invariant measure that captures the system's fate.
Oh, wow.
And they also prove that this measure is stable.
Okay.
Which means that the system will always be drawn towards it no matter where it starts.
So no matter how much we shake things up, the system's going to find its way back to this one predictable state.
Yes.
That's amazing.
It is.
But how do they even begin to prove all of this?
Yeah.
They must be using some pretty complicated math, right?
Oh, absolutely.
Yeah.
The paper relies on a whole bunch of sophisticated techniques from stochastic analysis, partial differential equations, and probability theory.
Okay, so to really understand these results, we need to break down the specific model that they're using, which is the stochastic Allen-Cahn-Navier-Stokes system.
Right.
And this system is represented by a set of equations that, frankly, can look pretty intimidating at first glance.
Yeah.
But let's break them down a little bit.
Sure, let's break them down. Let's start with the core equations that govern this system.
Right.
The first one deals with the evolution of the velocity field of our fluid, denoted by, little u.
Okay.
And it includes terms for things like viscosity, convection, pressure, and the interaction with the order parameter.
Okay.
And this interaction is captured by the term White, where W is what we call the chemical potential, the driving force behind phase separation.
So we're taking into account how these fluids are pushing and pulling on each other as they try to separate.
Precisely.
Okay.
The next equation, div U equals 0, is basically ensuring that the fluid volume stays constant. This is known as the incompressibility condition. It's kind of a fundamental concept in fluid dynamics.
It means we can't just like squeeze the fluid into a smaller space, right?
Right, exactly.
Okay.
And then we have the equation that describes how that order parameter changes over time. It includes, convection by the fluid flow, which is represented by Ucho, and a term involving W, which is reflecting how the chemical potential drives the separation of the fluids.
So it's like W is kind of dictating how the different components of the fluid want to rearrange themselves.
Exactly. Now, W itself is defined by the equation W equals Bork plus F.
Okay.
So here is a positive constant that governs diffusion, how the order parameter spreads out over time.
Okay.
And F, that's the derivative of what we call the potential function F,
right,
which dictates the system's preference for phase separation.
Right. Now, I remember the paper mentioned something about a singular potential. Can you explain what that is?
Sure. So a singular potential in this context refers to a potential function that becomes infinitely steep as the order parameter approaches the boundaries of its physically relevant range.
Okay.
So this steepness creates this strong driving force for the fluids to completely separate.
So it's like an invisible wall.
Yes.
That's keeping the fluids from mixing beyond a certain point.
Exactly. And this paper, it focuses specifically on a certain class of singular potentials that satisfy a set of assumptions.
Right.
And these assumptions, they ensure that the potential behaves in a way that's both physically meaningful, but also, importantly, mathematically tractable.
Okay, so let's dive into those assumptions.
Okay.
The first one, assumption A2, outlines, like the ground rules for this singular potential, right?
It does.
It states that f has to be a sufficiently smooth function on this interval, -1, 1.
Right.
Meaning it has enough derivatives that we can work with.
Right.
It also states that the derivative of f is an odd function, and that the second derivative is always positive within that interval.
You got it. Those conditions are ensuring that the potential has a unique minimum at 0 and becomes infinitely steep as we approach the boundaries of that interval, -1, 1.
Right.
And this guarantees that the order parameter, which represents the relative concentration of the fluids, stays within a physically meaningful range.
It's like saying the order parameter is trapped between these two walls that represent the pure states of the two fluids.
Exactly.
And it's energetically favorable for it to be as close to one of those walls as possible.
Precisely. And they even give a classic example of a singular potential that fits these criteria, which is what's called the logarithmic potential. And it's given by this, slightly complicated looking equation. Sub log sub r, 1 plus r ln 1 plus r plus 1r ln 1r sub 0 sub 2 sub 2 sup, where r represents the order parameter. And then you've got AC and sub 0 sub. Those are positive constants related to the temperature of the system.
Right. And, that equation might look a little scary.
Yeah.
But the key is really in those logarithmic terms, right?
It is.
As the order parameter approaches either -1 or 1, those terms just blow up, creating that steepness that we need at the boundaries.
Exactly. That's what makes it a singular potential. And the logarithmic potential is just one example.
Right.
You have a whole family of potentials that actually fit these criteria, each capturing different aspects of this phase separation behavior.
So it's like having a toolbox of potentials.
Yes.
Each one tailored to a specific type of fluid mixture.
Exactly. Now, besides these deterministic terms that we've been talking about, the model also includes randomness.
Right. We can't forget about the randomness.
Right.
So the paper makes specific assumptions about these noise terms.
It does.
To make sure that they don't just completely throw the whole system out of whack.
Right. So you have assumptions, A3 and A4, that specify the properties of these noise terms. I won't get into the details, but they're basically guaranteeing that the noise is, well behaved.
Okay, so they're setting some ground rules for the randomness to make sure that it plays nice with the rest of the equation.
Exactly. And the way they choose these noise operators can really affect the system's behavior.
Yeah.
Different types of noise lead to different patterns of phase separation.
Right.
And different long-term dynamics.
It's like saying the flavor of randomness can influence how the fluids mix and separate.
That's a great way to put it.
Right. Now, I know we're going to be talking about solutions to these equations, but first, I'm curious, can you tell us a little bit about these equations that deal with the boundary and initial conditions?
Sure. So those remaining equations are basically setting the stage for how the fluids behave at the boundaries of the container.
Right.
And they specify what the initial state of the system is. So, for example, the paper focuses on what's called the Dirichlet boundary condition for the order parameter. And that basically means we're fixing the value of the order parameter on the boundary.
So it's like pinning down the edges of a tablecloth, right?
Yes.
Which then influences how the wrinkles form in the middle.
Exactly.
Okay.
And then the initial conditions simply say, okay, here's the starting values for the velocity field and for the order parameter.
So we're telling the system, start here.
Start here.
On your journey.
Yes, exactly.
Right. Now, with these equations and assumptions in place, the paper dives into proving some remarkable results.
It does.
They start by establishing the existence and the uniqueness of a strong solution to the stochastic system presented in Theorem 3.5.
Right.
And this theorem, it really lays the groundwork for everything that follows.
Absolutely.
Right. It tells us that the system is well posed.
It does.
Meaning that it has a solution, and that solution is unique.
Right. We're not dealing with some mathematical phantom.
Right. We know that the system behaves in a predictable and mathematically sound way, even with all that randomness that's thrown in.
Exactly.
And this theorem holds for both Neumann and Dirichlet boundary conditions for the order parameter.
It does.
Which adds even more power to it, right?
Absolutely. So it makes it very versatile, applicable to a lot of physical scenarios.
Right.
So that's a very nice result to have.
The paper then presents Proposition 3.9.
Okay.
Which establishes a continuous dependence estimate.
Right.
Could you explain what that is and why it's important?
So a continuous dependence estimate tells us that small changes in the initial conditions of the system lead to small changes in the solution. So, if you just nudge the system a little bit at the beginning, it's not going to veer off wildly in some completely different direction.
So it's like the system is stable.
Exactly.
Stable.
Predictable.
Even with the randomness and these complex interactions.
Exactly.
Right.
That's exactly right.
Now, this proposition, it highlights the use of Ito's formula.
Right.
Which is a key tool in stochastic analysis.
It is.
Can you talk a bit more about its role in this context?
Sure. So Ito's formula is really essential for handling these stochastic differential equations. It gives us a way to differentiate functions of these random processes, taking into account the fact that they evolve randomly. So in this case, what it's doing is it's helping us analyze how the differences between solutions arising from different initial conditions actually evolve over time.
So it helps us understand how those differences propagate through the system and whether they amplify or dampen over time.
Exactly. That's a great way to put it.
Right.
And this proposition basically establishes a precise bound on how much the solutions can deviate from each other based on, those initial differences and the accumulated effects of randomness and nonlinearities.
It's amazing how we can quantify these relationships that are so complex. Now, the paper also provides a specialized version of this continuous dependence estimate, specifically tailored for Dirichlet boundary conditions in equation 3.18. Why is it worth highlighting this particular case?
Because remember, the Dirichlet boundary condition, where we're fixing the value at the boundary, it imposes these stronger constraints on how the system behaves. And so by tailoring that estimate to that specific boundary condition, we can get a sharper, more precise bound on how much those solutions can deviate from each other.
So it's like having a more fine-tuned instrument. For measuring the system's sensitivity to initial conditions under these specific circumstances.
And this refined estimate becomes really useful later on when they're proving the uniqueness and stability of that invariant measure under the Dirichlet boundary conditions.
It seems like everything is laid out very carefully.
It is.
Step by step to build up.
It's a very well-structured paper.
To these key results.
Yes.
Okay, so let's move on to, I think, what's the main event here? The invariant measures.
All right, let's do it.
The paper goes really deep into exploring the existence, the uniqueness, and the stability of these measures.
That's where the real meat of the paper lies.
Because these invariant measures are so important.
They are.
They give us a way to describe statistically where the system's going to end up, even with all that randomness,
Exactly. It's like figuring out the most likely long-term scenarios for how the fluids are going to arrange themselves. And the analysis kicks off in section 4 by establishing the existence of these invariant measures. And to do this, they introduce what's called a transition semigroup, which describes how the system evolves from one state to another over time.
So it's like a roadmap that's telling us how the system's probabilities change as time goes on.
That's a great way to think about it. Now, to actually prove the existence of invariant measures, they used what's called the Krylov-Bogoliubov theorem. And this theorem basically gives you a set of conditions under which a dynamical system will admit an invariant measure.
So it's like a checklist to figure out if our system will eventually settle down into this predictable statistical pattern.
Exactly. And a key step in applying this theorem is to establish what we call tightness.
Tightness. Okay, that sounds a little abstract. What does that mean?
Imagine herding cats. It's hard to keep them all together, right? So tightness, in this mathematical sense, basically means we can show that the probabilities don't just scatter all over the place and become impossible to predict. It's like preventing them from leaking out of the system as time goes to infinity.
So it's like keeping all the possibilities contained within a manageable space.
Exactly. And they use a combination of estimates on the moments of the solution and these things called compact embedding theorems for Sobolev spaces to prove this tightness.
So they're basically showing that the probabilities are well behaved and don't just run off to infinity.
Exactly.
And once they've established this tightness, then the Krylov-Bogoliubov theorem it just kicks in, right?
Yes, it kicks.
And it guarantees that there exists
at least
one invariant measure.
Yes.
Right? So that's a huge accomplishment, right?
It is.
We've proven that there's at least one
right.
possible statistical snapshot
yeah.
that describes the system's long-term behavior.
Right.
But they don't stop there.
No.
Right?
No, they don't.
They want to know, is it unique?
Right.
Is this invariant measure unique?
Right.
And if so, is it stable?
Exactly.
Yeah.
Those are the key questions.
And so they dive into these questions in sections 5 and 6.
Yeah, I do.
And we're going to have to unpack those in detail to really get into the guts of the uniqueness and stability argument.
Absolutely.
Right. So it seems like we've got a lot more ground to cover.
We do. We do. This is just the beginning.
Okay. Well, I'm excited to keep going.
Me too. We do. We do. This is just the beginning.
Okay. Well, I'm excited to keep going.
Me too. So in sections 5 and 6, the paper really dives into the uniqueness and stability of the invariant measure.
Okay.
And they start by introducing these, new spaces, 86 for argit, for done.
Okay, new spaces. What's the deal with 80 and 1?
So think of them as kind of refined versions of the spaces and arsas that we talked about earlier.
Okay.
Remember, 81 was the unit ball of the 8001.
Right, right.
So the space AT, it's a subset of arbors that contains order parameters denoted by Y that satisfy this additional condition.
Now that Samus function, that's related to the singular potential, right?
You got it. It's defined as CZ by CR plus C, where kappa C is a positive constant.
Right.
It basically quantifies how steep the potential is for different values of the order parameter. And as I gets larger, the control over the potential's growth becomes more stringent.
So INES contains order parameters that are not only bounded, but they also have some control over how fast the potential grows.
Exactly. Now, Lysis is defined as the intersection of V$ and ASIR.
Okay.
So this means that elements of Y's not only belong to ASIR, but they also possess a certain degree of smoothness captured by belonging to this Sobolev space V$1.
It sounds like DZOS is a club with a much stricter dress code than ESAR.
That's a great way to put it.
Only the smoothest order parameters get it.
Only the smoothest, yeah.
Right. Okay, so Section 5, it focuses on the support of the invariant measures.
It does.
And Theorem 5.2 basically says that any invariant measure, its support has to be contained within a specific subset of initial conditions.
That's right. So it's kind of like we're figuring out the regions where the system is most likely to settle in the long run.
Okay, so we're identifying those areas where the system's going to be hanging out.
Exactly. And they show that these regions are characterized by bounds on the norms of the initial velocity field and order parameter, as well as the integral of the potential function f. But it doesn't stop there. They go a step further and prove that these invariant measures actually have full support on a smaller subset, denoted by Zex times one way. So that means every point within the smaller region has a non-zero probability of being part of the system's long-term behavior.
It's like the system is an explorer.
Yes.
And it's going to check out every single nook and cranny of this particular subset.
Exactly.
Right.
That's right.
Okay, and all of this is achieved using a pretty clever combination of estimates on the moments of the solutions and properties of that singular potential.
That's right. It all comes together.
Right.
Right.
Okay, Section 5 also introduces this concept of ergodicity, which is super important for understanding the long-term behavior of these stochastic systems.
It is a key concept. It basically means that the long-term average behavior of the system is equivalent to the average behavior over all possible states.
So instead of having to watch the system forever, we can just look at the average over all its possible states to get a sense of its long-term behavior.
Exactly. And that's incredibly valuable when you're dealing with systems that have randomness baked in. Now, Theorem 5.3 specifically states that under certain conditions, there exists at least one ergodic invariant measure for the stochastic Allen-Cahn-Navier-Stokes system.
So we know there's at least one statistical snapshot that captures not just the long-term behavior, but also this property of ergodicity.
Exactly. It's a very powerful result.
Yeah. How do they prove that?
So the proof hinges on demonstrating, again, that tightness of the family of invariant measures.
Remember those cats?
Yeah, exactly. Those cats, we got to keep them all together.
And you got to keep those probabilities in check.
Yes. And to establish this tightness, they rely on a lot of the estimates that we've talked about, including those on the moments of the solution
Right.
and the properties of the singular potential.
Right. So it's all connected.
It is.
It's all building on itself.
Absolutely.
All right. And then we finally get to section 6.
Yes.
Where the paper really tackles,
it does,
I think, the most challenging part
of
proving the uniqueness and the stability of the invariant measure.
That's right.
Okay, so this is where things get, like, really serious.
This is where the heavy machinery comes in.
Right.
Yeah.
So what kind of tools do they use to tackle these questions?
So they use some really powerful techniques from the theory of stochastic dynamical systems, including something called generalized coupling.
Coupling. Okay.
Yeah.
I've heard of that. Can you refresh my memory?
Sure. So imagine we make 2 copies of our system.
Okay.
We link them together in a very specific way.
Okay.
And then we analyze their long-term behavior to see if they synchronize.
Good.
If they do, we can actually deduce some pretty powerful conclusions about the original system.
So it's like we're setting up a race
Yes.
between 2 versions of the system.
Exactly.
And we want to see if they end up at the same finish line.
That's a great analogy.
Right. Okay, so how do they implement this coupling approach?
Okay, so to implement it
in the paper,
they actually introduce what they call a modified system in section 6.2, where they add a control term to the Navier-Stokes equation.
So it's like giving one of the racers a little head start.
Yeah, it's like a nudge, a gentle nudge in the right direction.
Right, to see if it can influence the outcome.
Exactly. And they analyze this modified system very carefully.
Okay.
And it leads to this, crucial result in theorem 6.7, which gives us an estimate that governs the difference between the solutions.
It's measuring how far apart the racers are.
Precisely. And importantly, this estimate shows that that difference tends to decrease exponentially over time.
Ah, exponential decay.
Yeah.
So they're really being drawn together.
Exactly. Now, for this convergence to happen, we need certain conditions to be met.
Okay.
Condition 6.6 plays a crucial role here.
Right.
It places restrictions on these parameters, y and n.
Okay, remind me what those parameters represent.
So bi controls the diffusion in the Allen-Cahn equation.
Okay.
And n determines the dimension of the subspace where that control term is acting in the Navier-Stokes equation.
Right, okay.
What condition 6.6 is doing is basically ensuring that the dissipative effects in the system, which promote stability and smoothing, are strong enough to overcome the noise and the nonlinearities that tend to push the system towards chaos.
So it's like we're setting up the conditions for a successful race.
Yes.
We need enough, damping force to make sure they converge.
Yes.
And a good control strategy.
Exactly.
To kind of steer them in the right direction.
You got it. And once these conditions are met, theorem 6.7 is basically the tool we need to prove uniqueness and stability.
Okay.
They then apply this theorem to establish these key results in sections 6.3 and 6.4.
Okay, this is where the magic happens.
This is where the magic happens, yeah.
So theorem 6.12 stands out as a major accomplishment.
It does.
Because it establishes the uniqueness of the invariant measure for the stochastic Allen-Cahn-Navier-Stokes system under those Dirichlet boundary conditions.
That's right.
Well, what does this theorem tell us?
It basically says that under the given assumptions, including condition 6.6, and an additional assumption on the noise operator, g.allow, there's only one invariant measure for the system. And it goes on to show that this measure is also ergodic and has full support on that set K times Weyrach that we talked about earlier.
So no matter how many times we run that race, there's only one winner.
One winner.
And that winner has explored every corner of the racetrack.
They've seen it all.
Right. That's a pretty comprehensive result.
It is. It's very powerful.
So how do they prove this? I imagine the proof must be pretty involved.
Oh, it is. It's a real tour de force. It uses that coupling approach. It uses the estimates from theorem 6.7. And it also cleverly exploits properties of the noise terms.
It's like a perfectly choreographed dance.
It is.
Of mathematical techniques, all working together.
Working in harmony.
To reveal this system's, unique and stable fate.
Exactly.
Right.
It's beautifully put.
And then they don't even stop there.
No, they don't.
They go on to prove in theorem 6.14, the asymptotic stability of this unique invariant measure. Remind me what asymptotic stability means.
Okay, so it means that regardless of where we start the system, the probability distribution of the solution will always converge to this unique invariant measure as time goes to infinity.
So all roads lead to Rome no matter where you start.
Exactly. That's a great way to put it.
Right.
Okay.
So how do they demonstrate this convergence?
So the proof relies on theorem 6.5, which gives a general criterion for asymptotic stability.
Oh, okay.
And they leverage this really cool metric for measuring distances between probability distributions called the Wasserstein metric.
The Wasserstein metric. Okay, remind me what that measures.
Okay, imagine you have two piles of dirt representing two different probability distributions.
Okay.
The Wasserstein distance basically measures the minimum amount of work needed to transform one pile into the other.
Okay.
Where work is defined as like the amount of dirt moved times the distance it's moved.
So it's like finding the most efficient way to like reshape one probability distribution into the other.
Exactly.
Right.
And they use this metric to rigorously show that the probability distribution of the solutions to our system converges to that unique invariant measure.
So we know it's asymptotically stable.
It is.
Right.
Yes.
It's amazing how these really abstract, it seems like mathematical concepts.
It is amazing.
Give us these concrete insights.
It is. It's a testament to the power of these mathematical tools.
Into how these physical systems actually behave.
That's right.
Right.
Yeah.
Okay, so let's switch gears a little bit and delve into some of the mathematical machinery.
Okay, let's get into the nitty-gritty.
Yeah, behind these results, right?
Yeah.
The paper, it really leans heavily on these things called Foyers-Prodi estimates to establish the uniqueness of that invariant measure.
That's right.
Can you give us some insight into these estimates and why they're so important here?
Sure. So Foyers-Prodi estimates are these really powerful tools for analyzing the long-term behavior of what we call dissipative systems.
Okay.
Systems where energy is lost over time due to things like friction or viscosity.
Right, okay.
What these estimates tell us is that if we can control a finite number of key modes or components of the system, we can actually control the entire system's long-term behavior.
So if we keep a close eye on those most influential players, we can kind of predict the overall outcome.
That's a great way to put it.
Right.
Yeah.
Now, in the context of this particular system, the stochastic Allen-Cahn-Navier-Stokes system, these estimates come into play when we're looking at the difference between two solutions that started from different initial conditions.
Exactly. So we're looking at two versions of the system, each taking a slightly different path, and we want to see if they eventually come together.
Right.
The Foyers-Prodi estimates give us a way to actually quantify how clearly these two solutions converge.
Right.
They essentially say that if those solutions agree on a sufficiently large number of what we call low-frequency components, these are the components that capture the large-scale behavior of the system, then they will eventually converge to each other as time goes to infinity.
So it's like if the two racers in our analogy are neck and neck for the first few laps, they're probably going to end up finishing together.
Yeah.
Even if their individual strides might differ.
Exactly.
Right. Now, the paper establishes these Foyers-Prodi estimates in expectation.
It does.
Which means we're not looking at individual instances of the system.
Right.
But we're considering its average behavior.
Yeah, we're taking
over many different possible scenarios.
Oh, right.
Right. So we're taking into account that randomness.
That's right. It's a probabilistic approach.
So instead of trying to predict the exact path of each racer, we're analyzing their average positions over many different races.
Precisely. And this is really key for dealing with these stochastic systems where randomness is a big part of the game.
Right.
These Foyers-Prodi estimates and expectation are given in proposition 6.8.
Okay.
And they provide a bound on the expected value of a particular functional that captures the difference between solutions.
Right.
And this bound shows that this expected difference decays exponentially over time.
There's that exponential decay again.
There it is again.
Right. So the system wants to settle down.
It does.
And forget about its initial conditions.
Exactly. It wants to find that equilibrium.
Right. Okay. So for these estimates to work, we need to carefully balance the dissipative effects in the system.
Right.
Which are represented by those parameters against the strength of the noise and those nonlinearities that want to make things more chaotic.
That's right. We need to make sure the dissipation wins in the end.
Right. And that's where condition 6.6 comes in.
Exactly.
To make sure that the dissipation is strong enough to control the noise and the nonlinearities.
Exactly.
So it's like making sure the damping force in our race is strong enough to keep the racers from veering off course or getting too far apart.
Exactly. It keeps everything under control.
Right. It's amazing how we can control these systems.
It is amazing.
That seem chaotic.
Yeah.
Just by tuning a few parameters.
By carefully choosing those parameters.
Right. Now, to prove the uniqueness of the invariant measure, we also need this tool of generalized coupling.
Right.
Right. We talked about running those two systems in parallel.
Yeah, those two coupled systems.
How is that implemented in this paper?
Okay, so they implement it by introducing that control term in the Navier-Stokes equation that we talked about for one of the systems.
Right.
You know, like we saw in equation 6.9. This control term is designed to nudge them towards synchronization by exploiting the dissipative nature of the system and leveraging those Foyas-Prodi estimates.
So we're giving one of the racers a gentle push in the right direction.
A little nudge.
Right. And this allows us to analyze the convergence in a probabilistic sense.
Yeah.
Right. So how do they do that?
So to do that, they rely on a few key steps. First, they establish that the laws of the solutions to the original system and the modified system are actually equivalent on a specific subset of the space of trajectories.
What does laws of the solutions mean?
Okay, good question. The law of a stochastic process refers to its probability distribution. So we're basically saying that despite the differences in their equations, the original and modified systems actually have the same probability of following certain paths.
So even though the racers might have started differently and one has a bit of an advantage, they still have an equal chance of taking certain routes.
Exactly.
Right.
That's a great analogy.
And how do they establish this equivalence of laws?
They use a tool from probability theory called Grussonov's theorem.
Grussonov's theorem.
That's the one.
It allows us to relate the probabilities of those two processes.
Yes.
Right.
It does.
So we're kind of like shifting the odds in favor of convergence by carefully choosing that control term and applying Grussonov's theorem.
That's right.
Okay, so we've created this scenario where the systems are really likely to synchronize their long-term behavior.
Exactly. Now, once they've established this equivalence of laws, the next step is to show that the solutions to those two systems actually converge to each other along a specific sequence of times. So even though they may not be perfectly in sync at every single moment, they will meet up at certain checkpoints.
At these checkpoints? Along the way.
And these checkpoints are strategically chosen to exploit the dissipative nature of the system and to leverage those Foyas-Prodi estimates. So they look at the probability of the difference between the solutions exceeding a certain threshold. And by using the Foyas-Prodi estimates and the properties of those chosen stopping times, they show that this probability actually goes to 0 as time goes to infinity.
So the chance of the racers being far apart at these checkpoints just gets smaller and smaller.
Exactly. It becomes vanishingly small.
As the race goes on.
As the race goes on. That's right.
Right. Okay. And so this convergence is really the key.
It is.
To proving the uniqueness of that invariant measure.
It is.
Right.
That's right.
And this is what leads to theorem 6.1.
Exactly.
Which states that there's at most one invariant measure for this system.
Under those conditions.
Right. Under these conditions.
Yes.
So we've used this combination of tools.
We have.
The coupling. The Foyas-Prodi estimates, the stopping times, to show that the system will settle down into one well-defined statistical pattern.
It will. And that invariant measure is really capturing the essence of the system's long-term behavior.
Right. Okay.
It's a beautiful result.
It really is remarkable.
It is.
How all of these, different mathematical tools
they all come together
to create this powerful conclusion.
It's a symphony of mathematical ideas.
Right.
It is.
Okay, and then they take it even further.
They do.
They prove in theorem 6.14 the asymptotic stability of this unique invariant measure.
Right. So no matter where the system starts, it'll be drawn to this one unique state.
All roads lead to Rome.
Exactly.
Right. Okay, so how do they show that?
So they use theorem 6.5, which provides that general criterion for asymptotic stability. And they use the properties of the Wasserstein metric.
Right, that dirt pile analogy.
Exactly. To show that convergence in the space of probability measures.
This whole paper is like a symphony of ideas.
It is. It's beautifully done.
Each theorem, each proposition plays a crucial role in the overall composition.
Absolutely. It really highlights the power of mathematics for understanding these complex systems.
Right. Now, before we wrap up this deep dive into the math, I want to talk about the broader implications of these findings.
Okay, sure.
What excites you most about this work?
What excites me most is that this paper shows how powerful math can be for tackling these really tough problems in fluid dynamics. I mean, this stochastic Allen-Cahn-Navier-Stokes system, it's not a walk in the park.
It's not.
It's a challenging model.
It's a mouthful to even say.
It is. But we can actually analyze its long-term behavior with these really cool mathematical techniques.
So even though it seems chaotic,
yes,
there's actually an order underneath it all.
There is. There's an underlying order
that we can figure out.
And these invariant measures really give us a window into that order.
It's like finding the patterns.
Yes.
Amidst all the turbulence.
Exactly.
Right. Now, while this paper makes some real progress in understanding these systems,
it does.
It also points out some limitations.
It does.
And some areas for future research.
Right. There's always more to do.
What are some of those unanswered questions?
Okay, well, one thing that I'm curious about,
what do you find intriguing,
is how the system behaves under more general types of noise.
Okay.
So this paper focuses on a specific type of noise operator.
Right.
But what happens when we explore different kinds of noise?
Right, like adding different spices to the mix.
Exactly.
Seeing how it affects the overall flavor.
That's a great analogy.
Right.
Yeah. Another interesting direction is extending the emphasis to higher dimensions.
Right, because they looked at 2 dimensions.
We did.
But the real world is in 3 dimensions.
It is. So what happens in 3 dimensions?
Right, so it's like we're expanding the playground.
Yes.
And allowing for more complex patterns to emerge.
That's right.
Right. And what about different boundary conditions?
That's another great point. They focused on Dirlet conditions.
Right.
But what happens if we look at Neumann or Robin conditions?
So it's like exploring different terrains.
Yes.
Right? Each boundary condition
creates a different landscape.
Creates a different landscape for the fluids.
That's right.
Right. And understanding how those different landscapes affect things.
Yes.
Is a real challenge.
It is. It's a fascinating challenge.
But it could lead to some really interesting insights.
Absolutely.
Right.
Yeah.
It's incredible how these constraints that seem so simple.
They do seem simple.
Can have such huge impacts.
They really can.
Right.
It's what makes fluid dynamics so interesting. There's always more to learn.
Right.
Always another layer to peel back.
Well, this deep dive into the stochastic Allen-Cahn-Navier-Stokes system.
It's been a journey.
Has been incredible.
It has.
You know, we've explored this world of fluids and equations and some really elegant math.
Absolutely.
Right.
Yeah, it's been a pleasure joining you.
On this exploration.
It really has. And I think one of the things that I'm taking away from this is how much these abstract mathematical ideas actually have real world implications. I mean, we've been talking about oil and water.
Yeah.
But these ideas can be applied to so many other things.
Oh, absolutely. I mean, the techniques and the concepts that they've explored in this paper, you can apply those to all sorts of phenomena where you've got this mixing and separation and random influences.
Yeah.
Think about cloud formation, the dynamics of cell membranes.
Wow.
Even patterns in financial markets.
So it's like we've uncovered this hidden mathematical language that describes all this complexity around us.
I love that. That's a great way to put it.
Right. Now, before we wrap up, I'm kind of curious what really resonated with you personally.
What were some of your aha moments when you were reading this paper?
Well, for me, it was the coupling approach. I mean, it's just amazing how we can build these 2 systems that are linked together and use them to figure out how the original system behaves.
Like a mathematical magic trick.
It is. It is. We create this thing that seems totally artificial.
Right.
But it tells us these deep truths about the real world.
Right.
And the way they combine that with the Foyest-Prodi estimates and the Wasserstein metric, it's brilliant. It shows how creative mathematicians can be.
It's like watching a master craftsman.
Yeah, exactly. Using all these different tools to build something amazing.
Right.
You know, another thing that really got me thinking was that concept of ergodicity.
Oh, yeah.
I mean, the idea that the long-term average behavior of the system is connected to the average over all its possible states, it's powerful.
It's like, if we understand the statistics, we can understand where the system is going.
Exactly. And this isn't just about fluid dynamics either.
Right.
I mean, this idea applies to all kinds of fields.
Right.
Statistical mechanics, finance, even social systems.
It's a reminder that even when things seem chaotic,
Yeah.
There are still patterns underneath.
There are.
That we can discover.
And by understanding those patterns, we can make better predictions.
Right.
And we can understand the world better.
Well said.
Yeah.
This deep dive into the stochastic Allen-Cahn-Navier-Stokes system
It's been fun.
Has been amazing.
It has.
We've really gone deep.
We have.
Not just into the model,
yeah,
but into how mathematicians think.
Absolutely. And it's beautiful, isn't it?
It is. And for everyone listening out there,
yeah,
I hope you're feeling inspired.
I hope so too.
To keep learning and keep exploring.
That's what it's all about.
It's a whole universe out there waiting to be discovered.
There is.
And math is the key to unlocking its secrets.
It is.
So until next time, keep diving deep. Welcome back, everyone. Ready to dive into some seriously fascinating math today.
Absolutely. Always up for a challenge, especially when it involves fluids, randomness, and
invariant measures.
You got it. We're tackling this paper today. Existence, uniqueness, and asymptotic stability of invariant measures for the stochastic Allen-Cahn-Navier-Stokes system with singular potential.
Quite a mouthful. But hey, that's what makes these deep dives so fun, right? We get to break down complex topics into
bite-sized pieces.
Exactly. So essentially, this paper is looking at how two fluids mix when there are random forces at play. Like,
imagine oil and water in a blender, but
with a blender having a mind of its own, going at different speeds randomly.
That's a great analogy. So the question is, will this crazy mixing eventually settle into some kind of predictable pattern? And that's where the concept of invariant measures comes in.
These are like the attractors of the system, the states where it wants to settle down in the long run. And this paper claims that under specific conditions, there's only one such unique invariant measure.
Which means no matter how you start mixing those fluids, as long as you meet those conditions, they'll always end up in the same final state. Pretty amazing, huh?
Absolutely. But before we get too deep into the math, I think it's important to highlight why this even matters. I mean, who cares about invariant measures in a theoretical system?
Well, the applications are actually pretty wide-ranging. The paper mentions biology, material science, even
FLA geotherapy.
Right. Think about it. Understanding how fluids mix, even in a chaotic environment, can help us design more efficient processes, predict cell behavior, or even optimize medical treatments. The possibilities are quite exciting.
So we're not just messing around with equations here. This stuff has real-world implications. All right, so let's meet the characters of this mathematical play. We've got the order parameter denoted by phi, which basically tells us how mixed the fluids are.
Think of it as a value ranging from metago 1 to 1. Metago 1 and 1 represent the pure states of each fluid, like pure oil and pure water. Any value in between indicates mixing, with 0 being a perfectly balanced mix.
Makes sense. Then we have the usual suspects in fluid dynamics. The velocity field, U, and the pressure field, pi.
Describing how those fluids are moving and the pressure they're under. Classic fluid dynamics stuff.
But here's the twist. We're dealing with stochastic versions of these equations, meaning we're adding that element of randomness, which complicates things quite a bit.
Exactly. We can't forget about the chemical potential, WU, which also plays a role in how the fluids mix.
It's like a complex dance of variables all influencing each other.
Absolutely. To capture all this, we have the Cahn-Hilliard and Allen-Cahn equations, both in their deterministic and stochastic forms. And in this paper, we're focusing on the stochastic versions,
where the randomness really kicks in. Now, for our math enthusiasts out there, let's peek into the mathematical framework.
The paper works with specific function spaces, and a key player is the logarithmic potential function, denoted by f sub log sub r. It's defined as
f sub log sub r equals
f sub log sub r plus 1 r ln 1 1 plus 1 r ln 1 r plus sub 0 sub 2 sub, where r is the order parameter, phi, and it lies between -1 and 1. Theta and theta naught are constants related to the temperatures of the fluids, with 0 less than theta naught. This function essentially captures the energy associated with the mixing process.
So the energy involved depends on how much of each fluid we have, represented by r, and their temperatures. Makes sense, right? The hotter it is, the more energy involved.
Precisely. And this function dictates how easily those fluids will mix, something our listener definitely wants to consider when setting up their experiment.
It's like saying, hey, temperature matters just as much as how much of each fluid you're using.
Exactly. Now, another tool that's crucial in this analysis, weak topologies. These are special tools in functional analysis that help us study the long-term behavior of this system.
I bet you with your expertise on listeners' relevant field, you've come across these before.
Oh, definitely. Weak topologies allow us to see subtle convergence patterns that we might miss otherwise. It's like using a high-powered microscope to examine the intricate details of how these fluids mix.
I love that analogy. Now, to keep this whole mathematical party going, the authors lay down some ground rules, a set of assumptions.
They're labeled A1 through A7 in the paper. These assumptions aren't just random. They reflect real-world considerations about fluid behavior. For example, A1 sets the boundary conditions.
Meaning how the fluids interact with the walls of the container. Like saying, okay, we're assuming they can't escape, they're trapped.
Right. Then A2 outlines properties of our potential function, making sure it behaves in a physically realistic way.
No magical mixing here.
Exactly. A3 and A4 deal with the noise terms. We need to define how that randomness behaves mathematically.
Making sure the noise is well behaved so we can actually solve the equations.
Precisely. A5 and A6 are a bit more technical, dealing with the growth of the potential function's derivatives.
Ensuring the math doesn't spiral out of control.
Right. And finally, A7 is crucial. It guarantees that the noise is strong enough to push the system towards a unique equilibrium.
So the randomness isn't just a minor nuisance. It actually plays a key role in shaping the final outcome.
Exactly. It's like saying, hey, those random forces need to be powerful enough to really stir things up and lead to a unique final state.
Okay, so we've set the stage, introduced the players, and laid down the rules. What's next in this mathematical adventure?
Well, now we delve into the heart of it all, invariant measures. And we'll unpack how the authors go about proving their existence and, more importantly, their uniqueness in the next part.
All right, invariant measures. Now, these always kind of trip me up back in grad school. It's like they're these special states the system wants to settle into, right? Even with all the chaos.
Yeah, you're on the right track. Think of a pendulum swinging. Eventually it stops, right? Settles at the bottom. That's like its invariant measure.
So even though we're dealing with random forces messing things up, we're trying to find those resting points for our fluid mixing system.
Exactly. And this paper doesn't just stop at finding them. It aims to prove there's only one such point under certain conditions, meaning no matter how you start mixing, you'll always end up at the same final state.
That's a bold claim, like saying there's a predetermined destiny for these fluids. Okay, how do they even begin to tackle that? The paper mentions this thing called a transition semigroup, denoted by P.
Right. Think of it as a map showing how the system evolves over time. Each point on the map represents the system's state at a specific time.
So we can see how it goes from one state to the next, like a timeline of the mixing process?
Exactly. And the semigroup, P, encodes all the info about how the system transitions between states. All the dynamics, the randomness, it's all in there.
So crack the code of P, and you can predict the future of the system.
In a way, yes. And that's where properties like the Feller and sequential weak Feller properties become important.
Now those sound familiar. Vaguely. Refresh my memory.
They basically ensure that P behaves nicely. Meaning, no sudden jumps or weird discontinuities in the system's evolution. They make sure it evolves smoothly, even with the randomness.
Ah, okay. So even though things are chaotic, there's still some underlying order.
Precisely. These properties are proven in Lemmas 3.2 and 3.4, by the way, if you want to dive into the nitty-gritty.
I might just take your word for it this time. So how do we actually find these elusive invariant measures?
The authors use a clever technique, the Krylov-Bogolyubov method. It's like taking a long exposure photo of the system.
Okay, I'm intrigued. Explain that one.
We start with any initial state and let the system run for a long, long time. Then we average the system state over that whole period.
So we're blurring out all the short-term fluctuations and focusing on the long-term trend.
Exactly. We're hoping this average will reveal something about the invariant measure. And to make sure this averaging process actually leads somewhere, we need to prove something called tightness.
Tightness. Is that like making sure the average doesn't just fly off into infinity?
You got it. It means the measures stay within a bounded region of the state space, so we're not chasing a ghost.
Right. The average needs to actually represent something real.
Exactly. That's proving existence. But for uniqueness, the authors get even fancier. They use something called the generalized coupling method.
Coupling? Is that like linking two systems together?
You're sharp today. Imagine two copies of our system, each starting from different points. Coupling is like creating a subtle connection between them, a way for them to talk.
So they start off doing their own thing, but then this coupling nudges them towards each other.
Exactly. The goal is to make them synchronize eventually. If any two starting points, when coupled, lead to the same final state, we've essentially proven there's only one unique endpoint.
So no matter where you start, you end up at the same destination, like all roads lead to Rome. But how do you actually couple these systems?
They create a modified version of the system with a control mechanism. It's based on something called Foyas-Prodi estimates.
Now, those sound vaguely familiar, but I'm drawing a blank.
They're a way to figure out how much control we need to apply to the system to make those copies synchronize.
Control meaning?
What, exactly?
We need to control certain modes of the velocity field. Think of them as the dominant patterns or frequencies in how the fluid is moving. Force those to match, and the rest will follow.
So if we get the big picture right, the details will sort themselves out.
Precisely. The beauty of Foyas-Prodi is that we can actually calculate how many modes to control based on the system's parameters. It's not just a guess.
So it's like, hey, to synchronize these systems, just tweak these specific things and you're good to go.
Right. This control is added as a specific term in the Navier-Stokes equation for the modified system. It's like a gentle nudge in the right direction.
Okay, so we've got this modified system. It's being steered towards the original one. But how do we know they're actually getting closer? How do we measure that?
Well, the authors need to prove this crucial inequality, which relates to the solutions of both systems.
So we need a way to quantify how close they're getting. You got it. That's where proposition 6.8 comes in. It's a powerful estimate that connects the difference between the solutions of the two systems to the initial difference and a special weighting factor.
Sounds complicated.
It is, but it's the cornerstone of the uniqueness proof. The inequality involves the expected value of a weighted difference between the original system and the modified system. Ooh.
Hang on. Lots of symbols there. Walk me through it.
So we're looking at x plus x sub 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 sub. This is less than or equal to the initial difference. Os up sub 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 plus x up sub 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 sub. Essentially, it tells us that the weighted difference between the solutions at a given time is bounded by their initial difference.
Okay, taking it step by step. We're comparing the order parameters, phi tilde and phi, and the velocity g tilde u of both systems.
Right. Using norms specific to their function spaces, we're quantifying how different their mixing states and velocities are.
Got it. And what about that exponential term in the inequality?
That's like a discount factor. It lessens the impact of the differences as time goes on. Is a special function based on the system's parameters, and sun is a stopping time, kind of like a safety net.
Safety net.
In these systems, solutions can sometimes become unbounded, like they grow infinitely large. That messes up our calculations.
Yeah.
So it is a way to pause the analysis if things get too wild.
Makes sense, like saying, whoa, hold on, things are going haywire, let's reassess.
Exactly. It keeps our analysis grounded. So this inequality, it's basically telling us that the coupling is pulling the two systems closer together, no matter how different they started.
Like a magnetic force, bringing them into harmony.
A good way to think about it. But to really seal the deal on the uniqueness, we need a bit more. That's where the Gersonov theorem comes in.
Oh yeah, you mentioned that earlier. Another one of those powerful math tools.
Specifically, proposition 6.3. This theorem allows us to relate the solutions of the original and modified systems in a probabilistic way. We're essentially building a bridge between them, using probabilities as the building blocks.
Probabilities, how does that work?
It's a bit technical, but essentially, the Gersonov theorem lets us shift the underlying probability measure of the system in a controlled way, taking into account the control mechanism we've introduced. We can then show that what happens in the modified system can also happen in the original system, probabilistically speaking.
So we're not changing the fundamental nature of the original system, we're just guiding it subtly with this modified version.
Exactly. And this connection is key to bridge the gap between the Foyas-Prodi estimates, which only guarantee convergence at specific times, and the continuous time convergence we need for the final proof.
So it's like smoothing out the convergence process, making sure it's not just happening in jumps, but continuously over time.
Precisely. Now, we need one final piece of the puzzle theorem 6.2. This comes from ergodic theory, and it basically says, if we can find a set of initial conditions where the two systems converge with some positive probability, then there can only be one invariant measure for the entire system.
So if we see a glimmer of convergence somewhere, That glimmer applies to everything.
Exactly. And the Foyas-Prodi estimates, with the help of the Gersonov theorem, provide that glimmer. They guarantee that for a large enough set of starting points, the two systems will converge with a positive probability.
It's like finding a single working key and realizing it unlocks every door in the castle.
A perfect analogy. So combining this convergence property with theorem 6.2 leads us to the conclusion. This system can have, at most, one invariant measure.
Wow, so we're really close to proving uniqueness. What's next?
Well, the authors go a step further. Theorem 6.14 proves the asymptotic stability of this invariant measure.
Asymptotic stability. That sounds like the system not only settles down, but also does it in a specific way.
You got it. It involves something called the Wasserstein metric, which measures the distance between probability distributions.
Ah, right. So we're not just saying it converges, but also specifying how it approaches that final state.
Precisely. Theorem 6.14 guarantees that no matter where you start, the system will get arbitrarily close to the invariant measure over time, according to this Wasserstein metric.
So it's not just a random settling down, it's a controlled approach towards this unique equilibrium.
Exactly. And the proof utilizes the Foyas-Prodi estimates again, along with another result from ergodic theory, Theorem 6.3.
This is incredible. We've gone through so much. From setting the stage to understanding these complex techniques, it's been quite a journey.
Indeed. But the story doesn't end here. We still need to put all these pieces together to see how they conclusively demonstrate the uniqueness of the invariant measure. And that's what we'll do in the final part.
Okay, so we've built up all this mathematical machinery. We've got Foyas-Prodi estimates, the Gersonov theorem, this modified system with a control mechanism. How do all these pieces fit together to finally prove that there's only one unique invariant measure?
It's like the grand finale, right? All the storylines converge. The key lies in showing that this controlled convergence we've achieved with the modified system actually translates to convergence in the original system.
Ah, okay. So the modified system is like our training ground, but the real test is whether that training pays off in the real world, the original system.
Exactly. And the bridge between these two worlds is, once again, the Gersonov theorem, proposition 6.13 specifically.
Right, that theorem that lets us connect the solutions of the two systems using probabilities. I'm starting to see how powerful this theorem is.
It's a real workhorse in this paper. It allows us to show that the modified system can't do anything too crazy, probabilistically speaking, that the original system couldn't already do.
So we're not fundamentally altering the behavior by adding that control mechanism. We're just nudging it in the right direction.
Precisely. And this connection is crucial because the Foyas-Prodi estimates only guarantee convergence at specific times. But Theorem 6.2, which we need to use, requires continuous time convergence.
Ah, so the Gersonov theorem helps us smooth out the convergence, making sure it's not just happening in jumps, but continuously over time.
Exactly. Now, Theorem 6.2, this gem from ergodic theory, tells us something incredibly useful. If we can find just one set of initial conditions where the solutions of the two systems converge with some positive probability,
then there can only be one invariant measure for the whole system. I remember you mentioning that earlier. It's like if we see a glimmer of convergence somewhere, that glimmer applies everywhere.
That's the beauty of it. And guess what provides that glimmer? Our trusty Foyas-Prodi estimates combined with the Gersonov theorem. They guarantee that for enough starting points, the two systems will converge with positive probability.
So we've found our needle in the haystack, that one set of initial conditions where convergence is guaranteed.
And that one needle unlocks the entire system. Leads us to conclude that the stochastic Allen-Cahn-Navier-Stokes system can have at most one invariant measure.
Wow, this is a huge accomplishment. We've climbed the mathematical mountain and reached the peak. Uniqueness of the invariant measure.
But wait, there's more. Theorem 6.14 doesn't just stop at uniqueness, it proves something called asymptotic stability.
Okay, more mountain climbing then. What does asymptotic stability mean?
It means that the system not only converges to that unique invariant measure, but it does so in a specific way, measured by the Wasserstein metric.
Ah, right, the Wasserstein metric, our special ruler for measuring distances between probability distributions. So we're not just saying it settles down, we're saying how it approaches that settled state.
Precisely. Theorem 6.14 guarantees that the distribution of the solution, no matter where you start, gets arbitrarily close to the distribution of that invariant measure as time goes to infinity.
It's like a turbulent sea slowly calming down, all the waves settling into a perfectly still surface.
And the proof of this theorem, once again, relies on our Foyas-Prodi estimates, along with Theorem 6.3 from ergodic theory.
This has been an incredible journey. We've delved deep into the math, unpacked these sophisticated techniques, and emerged with a profound understanding of how this chaotic system behaves in the long run.
And it's not just a theoretical exercise. The insights from this paper have implications for so many fields. Imagine using this knowledge to design better mixing processes, predict cell behavior, even revolutionize medical treatments.
It's amazing how such abstract math can have such tangible impacts on our world.
That's the beauty of it, right? The power of mathematics to uncover hidden order within chaos and pave the way for innovation.
Absolutely. Well, that brings us to the end of our deep dive into the world of stochastic fluid dynamics. We've explored the depths of this paper, and hopefully our listeners have gained a new appreciation for the elegance and power of mathematics.
And who knows, maybe some of you will be inspired to take these ideas even further, push the boundaries, and discover new mathematical treasures.
That's what we hope for. Until next time, keep exploring, keep questioning, and keep the mathematical spirit alive. Welcome back, everyone. Ready to dive into another fascinating paper?
Always. What are we exploring today?
Well, today we're looking into multi-component fluids.
Ah, interesting. Multi-component fluids.
Yeah. Those systems, where you have like different fluids all mixing and interacting together.
Right. Like oil and water or...
Exactly, yeah. Or like mixtures in like chemical reactions or even in biological systems.
Okay, I'm starting to get the picture. But I imagine analyzing these systems gets pretty complicated pretty fast.
Oh, you have no idea. And the paper we're diving into today, it really goes all out. It uses some pretty heavy-duty mathematical tools. Specifically, they're looking at something called the stochastic Allen-Cahn-Navier-Stokes system.
Stochastic Allen-Cahn-Navier-Stokes. Okay, that's a mouthful.
It is. But don't worry, we'll unpack it all bit by bit. So to start off, let's talk about the approach they use to model these fluids. It's called the diffuse interface approach.
Diffuse interface. Okay.
Yeah, so instead of thinking of those fluids as having like a clear-cut boundary between them, like a hard line separating oil and water,
right,
they imagine a smoother, more continuous transition zone.
I see. So like a blending zone rather than a sharp dividing line.
Exactly. And to describe this blending, they use something called an order parameter, usually denoted by the Greek letter phi.
Okay, so it tells us something about the composition of the mixture at any given point.
Yeah, precisely. Like if equals 1, it means it's all one fluid, say all oil. If is minus 1, it's all the other fluid, all water in our example.
And values in between represent different degrees of mixing.
Exactly. Now, to keep things physically realistic, the paper introduces what's called a logarithmic potential, which they give an equation 1.1. Have you had a chance to glance at that equation yet?
I have, yeah. It looks a bit intimidating, but I think I'm starting to get the gist of it.
Great. Basically, this potential ensures that our order parameter stays within that meaningful range of -1 to 1. It's like a mathematical constraint that prevents from going haywire.
Makes sense. You can't have more than 100% of a single fluid in a mixture.
Precisely. It ensures that the model behaves in a way that, actually reflects reality. Now, getting to the heart of it, this stochastic Allen-Cahn-Navier-Stokes system, it's not a walk in the park, let me tell you.
I was about to say, with a name like that, it's got to be pretty complex.
Oh, it is. The paper lays it all out in equation 1.2, and it's a beast of an equation. But it's fascinating because it describes how the velocity, pressure, and that composition, they all evolve over time in this fluid mixture.
I'm seeing terms in there for velocity, pressure, viscosity.
Wait.
What, is that noise I see too?
You're sharp. Yes, those noise terms represented by W1 and W, those are really crucial here. They model the random fluctuations that are always present in any real-world system, really.
Right, because things are never perfectly predictable. There's always some element of randomness at play.
Exactly. And those G1 and G2 functions you see, they're there to control how those random forces influence the velocity and the mixing process itself. It's all about striking that balance between the deterministic laws of fluid dynamics and the inherent randomness of the real world.
I'm really intrigued by how they managed to capture both of those aspects in a single mathematical framework.
Me too. Now, the heart of the paper lies in figuring out what happens to this complex system in the long run. Like, how does it behave over time? That's where the concept of invariant measures comes into play.
Invariant measures. Okay, now we're getting into the really deep stuff.
We are. It's a bit abstract, so bear with me. Even though the system's constantly fluctuating because of that noise, there might be some statistical patterns that emerge over very long periods.
So even with all the randomness, there could be some underlying order, some stable trends that we can identify.
Exactly. And an invariant measure, think of it as a probability distribution that doesn't change over time, even though the system itself is constantly in flux.
That's a tricky one. It's like the system itself is dancing all over the place, but the overall probabilities of being in certain states remain constant.
That's a great way to put it. Now, this paper sets out to prove that these invariant measures actually exist for this stochastic Allen-Cahn-Navier-Stokes system.
Okay, so they're trying to show that even with all this complexity and randomness, the system might settle into some kind of predictable pattern, at least in a statistical sense.
Exactly. And under certain conditions, they want to demonstrate that there's only one unique invariant measure. Like, no matter where you start the system off, it'll eventually end up being described by the same statistical distribution.
Now, that's a bold claim. I'm guessing they need some seriously powerful mathematical tools to pull that off.
Well, they do. They use things like the Krylov-Bogolyubov method, generalized coupling techniques. It's really impressive stuff.
Krylov-Bogolyubov coupling techniques. I'm familiar with those in principle, but I'm really curious to see how they apply them in this specific context. It sounds like it could get pretty hairy.
Oh, it does. And this system poses some unique challenges, too. That logarithmic potential we talked about. It has this singular nature. It blows up at the boundaries, which creates some hurdles in the proofs. To overcome these, they need what's called a sufficiently large viscosity, represented by the Greek letter beta.
So the viscosity acts like a sort of dampening force, preventing the system from spiraling out of control because of those singularities.
That's a good way to think about it. And it's important to remember that all these mathematical marvels, they only hold true under certain conditions, which the authors lay out in their assumptions.
Right, the assumptions. Those are always crucial in any mathematical proof.
Absolutely. They're like setting the ground rules, ensuring that the mathematical model we're working with actually reflects the real-world behavior of these fluids.
So what kind of assumptions are we talking about here?
Well, to start, assumption A2, it focuses on that potential function, the one that keeps in check. It basically requires that the derivative of that function, denoted by f prime of r, blows up as r approaches those boundaries of mod equal 1 and 1. That's like reinforcing that guardrail we talked about, making sure the order parameter stays within physically realistic bounds.
Okay, that makes sense. So it's all about keeping the model grounded in reality.
Precisely. And then we have assumption A3, which deals with that noise term G1, the one affecting the velocity. It requires G1 to be bounded, meaning the noise can't cause those infinitely large, crazy jumps in the velocity. And it also has to be Lipschitz continuous. Have you ever come across Lipschitz continuity before?
Vaguely, yeah. It has something to do with how much a function can change over a given interval.
You got it. Basically, Lipschitz continuity means that the noise can't change too abruptly. It ensures that small changes in the system state don't lead to ridiculously large changes in the noise. It helps keep things smooth, relatively speaking.
Okay, so another way of keeping the model well-behaved and realistic. No sudden, infinitely fast fluctuations allowed.
You got it. And then assumption A4, it specifies the form of the other noise term, G2, the one acting directly on the order parameter. It basically ensures that that noise doesn't push outside of that crucial Huygens 1-to-1 range.
So all these assumptions, they're about setting the stage, making sure our mathematical model is playing by the rules of the physical world.
Exactly. They're crucial for ensuring the rigor of the proofs and, the meaningfulness of the results themselves. But I'm sure your head is spinning a bit already with all these concepts and assumptions.
A bit, yeah. But it's the good kind of spinning, the kind that makes you realize just how much depth there is to these seemingly simple phenomena.
I agree. And we've only just scratched the surface. Now, before we go any further, I'd love to hear your thoughts. What's been the most mind-blowing concept we've encountered so far?
That's a tough one. I think for me, it's the idea that even in a system as complex and inherently random as this, we might actually be able to say something concrete about its long-term behavior. The fact that they're trying to prove the existence of a unique invariant measure, it suggests that there's an underlying order amidst all that chaos.
I completely agree. It's like finding a compass in the middle of a swirling storm. But before we get completely swept away by that conceptual storm, let's move on to the key findings of the paper. What did they actually manage to prove about this system's long-term behavior?
Well, they start by establishing the existence of invariant measures, which they lay out in Theorem 5.2. So that's step one, proving that, statistically speaking, the system can indeed settle into these long-term patterns.
That's a big step, but I'm guessing they didn't stop there.
You're right. They go a step further in Theorem 5.3 and prove the existence of ergodic invariant measures.
Ergodic. Now, there's a word I haven't heard in a while. Could you remind us what that means?
Of course. Ergodicity, it's a pretty powerful concept when you're studying dynamical systems. It tells us that if you observe a system for a really, really long time, you'll essentially see all the possible behaviors it can exhibit, and you'll see them in the correct proportions as dictated by that invariant measure.
So it's like saying that over the long haul, the time average of the system's behavior is the same as the average over all possible states, weighted by the invariant measure.
Precisely. And that has some really interesting implications. It suggests that if we understand that invariant measure really well, we can gain a deep understanding of the system's long-term statistical behavior.
That's incredible. It's like having a statistical roadmap for a system that's inherently unpredictable on a moment-to-moment basis.
It is. But remember, we were talking about uniqueness earlier. Did they manage to prove that there's only one invariant measure, at least under certain conditions?
They did. And that's where Theorem 6.12 comes in. They show that if you have something called Dirichlet boundary conditions, that means the order parameter is fixed at specific values on the boundary of your container.
Right.
And if the viscosity that this view is talking about is large enough, then boom, the system has a unique invariant measure, like a mathematical prophecy.
So under the right circumstances, no matter where that system starts, it's statistically destined for the same ultimate fate.
Exactly. And to make things even better, they also proved the stability of this unique invariant measure. That's Theorem 6.14. Basically what it means is that regardless of the initial state, the system will actually converge to that unique statistical pattern over time. It's not just a theoretical possibility, it's an inevitable outcome.
So it's like a point of attraction for the system's long-term behavior. No matter where you started off, it's drawn towards that unique invariant measure.
Exactly. And the way they prove these results is quite remarkable. They use a combination of techniques like the Ito lemma, continuous dependence estimates, tightness arguments. They even pull out the Gersonov theorem. It's a real tour de force of mathematical ingenuity.
Wow, it sounds like they pulled out all the stops from their mathematical toolkit. I'm definitely eager to delve deeper into those proof highlights.
Me too. But before we get lost in the mathematical weeds, I think we need a moment to just process everything we've learned so far. This is some seriously mind-bending stuff.
I agree. We've gone from diffuse interfaces and order parameters to invariant measures, ergodicity, and asymptotic stability. It's been quite a journey.
It has. And we're only just getting started. I can't wait to see what other mathematical marvels await us in the next part of our deep dive.
Me neither. This is definitely one for the math enthusiasts out there, ready to venture a bit deeper into the mathematical jungle of this paper.
Absolutely. I'm particularly curious about how they actually prove these remarkable results. You mentioned the Krylov-Bogolyubov method, weak topologies, coupling techniques. It all sounds incredibly abstract and powerful.
It is. And the way they weave all these techniques together in the proofs is, well, it's quite beautiful, actually. Let's start with Theorem 5.2, where they use the Krylov-Bogolyubov approach to establish the existence of those invariant measures. Remember, this method is all about taking averages over time.
Right, like creating a mathematical time lapse to see if any patterns emerge from the apparent randomness.
Exactly. But there's a subtle twist here. Instead of directly averaging the solutions themselves, like, the actual values of the velocity or the order parameter, they average the probability distributions associated with the solutions at different points in time.
Okay, so we're averaging probabilities rather than actual values. I'm not sure I quite follow why that's important.
It's a clever trick that allows them to work in a space where they have some nice compactness properties. How can I explain this? Imagine you have a huge, unbounded space.
Okay.
It's hard to guarantee that a sequence of points in that space will converge to a limit. They could just keep spreading out forever. But if you can restrict yourself to a smaller, compact space, one where everything is nicely bounded, convergence becomes much more manageable.
So by averaging probability distributions, they're essentially creating a more well-behaved mathematical playground where it's easier to find those elusive invariant measures.
Precisely. And that's where the concept of weak topologies comes in. a weak topology, you see. It gives you a kind of coarser way of looking at convergence.
Coarser? What does that mean exactly?
Well, it means we relax the conditions for convergence a bit. Instead of demanding that the sequences converge point-wise, meaning every single point has to match up in the limit.
Right.
We only require that certain averages converge.
I see. So it's like saying we don't need every detail to perfectly match up, just the overall trends. This seems like a pretty clever way to deal with the inherent randomness of the system.
It is. By using these weak topologies, they can exploit the averaging that's built into the Krylov-Bogoliubov method and extract that invariant measure as a limit.
Okay, that makes sense. Yeah. But proving existence is only half the battle, right? They also want to show that this invariant measure is unique under certain conditions. And that's where you said the coupling techniques come in.
Exactly. And to set the stage for coupling, they need a powerful tool called the Fourier-Prodi estimate. This estimate basically tells us under what conditions controlling just a finite number of low modes of the system guarantees that two solutions, even if they start from completely different initial conditions, will eventually converge.
Low modes. I'm guessing those represent sort of the dominant patterns in the fluid's motion.
You got it. Imagine you decompose a complex wave into a bunch of simpler sine waves.
Okay.
The low modes correspond to those long, slow-moving waves that carry most of the energy. And the Fourier-Prodi estimate, what it's saying is, if we can somehow synchronize those dominant patterns, the rest of the system, all those little details, will eventually fall in line.
So it's like saying control the big waves, and the little ripples will sort themselves out.
Precisely. But how do they actually prove this Fourier-Prodi estimate? Well, it all hinges on the fact that this system is dissipative. Remember all that friction we talked about earlier, embodied by that viscosity term?
Right, the viscosity acts like a brake, causing the system's energy to dissipate over time. But I'm not sure how that helps with convergence.
Think of it this way. Imagine you have two solutions, each like a boat rocking back and forth on a turbulent sea.
Okay.
That viscosity acts like water resistance, gradually slowing down those rocking motions.
Mm-hmm.
If you also manage to synchronize the largest rocking motions, those low modes, the boats will eventually settle into the same gentle sway.
I love that analogy. It really helps to visualize how that dissipation, combined with control over those low modes, can lead to convergence. But there's still a piece missing, isn't there? How do they actually ensure that those solutions synchronize on those low modes in the first place?
That's where the coupling magic comes in. They construct two versions of the system, but they couple them together in a very special way that forces their low modes to agree.
I see. So it's like we're rigging those boats in your analogy to rock and sink from the get-go.
Exactly. And then that viscosity, along with that Fourier-Prodi estimate, they do the rest, gently guiding those solutions towards the same final state. But it's important to note they don't just want to prove convergence in some vague, hand-wavy sense. They want to show that those solutions converge with respect to a very specific metric, a way of measuring the distance between probability distributions.
And that metric is the Wasserstein metric, right? Didn't we explore that in a previous deep dive? Something about moving piles of dirt?
You have an excellent memory. The Wasserstein metric, also known as the Earth mover's distance, it gives you a very natural way to quantify how different two probability distributions are. In this case, it's measuring how far apart the statistical behaviors of those two solutions are.
So if that Wasserstein distance between two solutions shrinks down to 0 over time, it means their statistical behaviors are becoming indistinguishable.
Exactly. And the authors prove that under the conditions of Theorem 6.12, those Dirichlet boundary conditions and a sufficiently large viscosity, the Wasserstein distance between any two solutions really does converge to 0 as time marches on to infinity.
Wow. That's a powerful statement.
Yeah.
It means that the long-term statistical behavior of the system is completely determined by that unique invariant measure, regardless of where you started off.
Precisely. And to prove this convergence result, they use a really fascinating combination of techniques. There's a weighted continuous dependence estimate, some clever Ito calculus, and even a very slick stopping time argument.
Okay, now you're just showing off. Weighted continuous dependence estimate. What in the world is that?
It's like a souped-up version of those standard continuous dependence estimates we were talking about before. Remember, those estimates tell us that small changes in the initial conditions lead to small changes in the solution.
Right. It's like saying the system isn't overly sensitive to its starting point.
Exactly. But in this case, they introduce a special weight function that emphasizes the importance of those low modes.
I see. So it's like giving those dominant patterns extra weight in the convergence process. Why is that so important?
It allows them to really leverage the power of that Foyas-Prodi estimate. By zeroing in on those low modes, they can get much tighter control over the rate at which those solutions converge.
It's like fine-tuning the convergence engine, making it even more efficient. Okay, and what about this Ito calculus you mentioned? I vaguely remember Ito's lemma from my stochastic calculus days, but I'm drawing a blank on how it applies here.
They use the Ito lemma in a very ingenious way to derive some crucial energy estimates for the system. These estimates help to bound the moments of the solution, which is essentially a way of controlling how wild those random fluctuations can get.
So it's another mechanism for taming the chaos inherent in the stochastic system.
Precisely. And then to really clinch the uniqueness and convergence results, they use a stopping time argument. Basically, they define a stopping time that says, hey, if the Bosserstein distance between those two solutions ever exceeds a certain threshold, hit the pause button. By carefully analyzing the probability of this stopping time being finite, they can demonstrate that it's incredibly unlikely for those solutions to ever stray too far apart.
So it's like setting up a safety net to prevent the solutions from diverging too much. It all sounds incredibly intricate and ingenious.
It is. And we haven't even touched on the delicate interplay of probability bounds, Sobolev embeddings, and Gronwall's inequality that they sprinkle throughout the proofs. But I think the key takeaway here is these sophisticated mathematical tools, they allow them to extract order and predictability from a system that, at first glance, seems overwhelmingly random and complex.
It really is remarkable how they bridge that gap between this abstract world of mathematical concepts and the messy reality of fluid dynamics. But before we disappear completely down the rabbit hole of technical details, I think it's worth taking a step back. Why are these results so significant? What are the broader implications, beyond just the pure math?
That's a great question. This kind of research, it has the potential to impact our understanding of all sorts of real-world phenomena where you have randomness and complex interactions happening. Think about climate modeling, financial markets, or even the spread of diseases.
Right.
By developing these powerful mathematical frameworks for analyzing these kinds of systems, we can potentially gain real insights into their long-term behavior. We might be able to identify tipping points or even come up with strategies for controlling or mitigating unwanted outcomes.
That's a really powerful thought. It suggests that even in the face of all this complexity and uncertainty, there might be some underlying principles that govern the behavior of these systems, principles that we can uncover through the sheer power of mathematical analysis.
It's a humbling thought, isn't it? That even in the face of all this apparent chaos, there might be a hidden order waiting to be discovered. But as with any groundbreaking research, it also opens up a whole new set of questions and challenges.
Absolutely. For instance, you mentioned earlier that the paper focuses on the 2D case. What happens when we try to move to the 3D world? Does everything still hold true?
Now that's the million-dollar question, and unfortunately, it's not an easy one to answer. While many of the basic concepts and techniques can be extended to 3D, the mathematical analysis gets much, much tougher. For one thing, certain inequalities that are essential to those 2D proofs, things like the Ladies-in-Skaya inequality, they don't have direct analogs in 3D.
So it's like the rules of the game change when we add that extra dimension. The tools we used in 2D just aren't powerful enough to handle the 3D case.
Exactly. And the Navier-Stokes equations themselves, they become far more difficult to deal with in 3D. Turbulence, that chaotic, unpredictable, swirling motion we often see in fluids.
Right.
That becomes a major headache. It's like going from a beautifully choreographed dance to a mosh pit.
I love that analogy. So extending the results of this paper to 3D, it would probably require a whole new set of mathematical tools and insights.
Most likely, yes. It's a really active area of research, one that's constantly pushing the boundaries of our understanding of fluid dynamics.
It's exciting to think that there are still so many mysteries to be solved, even in a field that's been studied for centuries.
I agree. And even if we stick with the 2D case, there are still plenty of avenues to explore. Remember, the authors made some very specific assumptions about those noise terms in their model. What happens if we relax those assumptions? What if we allow for different types of randomness?
Right. They'd assumed that the noise was additive and that it acted on enough of those low modes to guarantee convergence. But what if the noise were, say, multiplicative, meaning its strength depended on the current state of the system? Or what if it didn't act directly on those crucial low modes?
Those are great questions. If the noise were multiplicative, it would introduce a whole new level of complexity. The dynamics of the system could change drastically. We might see multiple invariant measures pop up, Or maybe the system wouldn't converge to a stable pattern at all.
So it's like the noise could become this more active player in shaping the system's evolution, making its fate even more unpredictable.
Precisely. And if the noise didn't act directly on enough of those low modes, we might lose that crucial control mechanism that's driving convergence. That Foyas-Prodi estimate might no longer apply, and the whole delicate balance of the system could be thrown out of whack.
It's a reminder that the details really matter in these models. Even seemingly subtle changes can lead to entirely different outcomes.
Absolutely. Exploring those kinds of what-if scenarios where we tweak the noise structure, that's a fertile ground for future research. And it could have implications far beyond fluid dynamics, too. It could help us understand the behavior of complex systems across a wide range of fields.
Well, this deep dive is definitely giving me a whole new appreciation for the power of mathematics to reveal hidden patterns in seemingly chaotic systems. And it sparked a bunch of new questions that I'm definitely going to be pondering for a while.
I know what you mean. It's been an incredibly stimulating journey so far. And believe it or not, there's still more to come.
Okay, phew. I think I finally wrapped my head around all those complex concepts.
It's a lot to absorb, isn't it? But that's what makes exploring these cutting-edge research papers so rewarding.
It really is. It's intellectually challenging, but ultimately it's so satisfying to see how these brilliant minds are pushing the boundaries of our understanding.
I couldn't agree more.
Yeah.
Now, you mentioned earlier that the paper focused specifically on the 2D case of this Allen-Cahn-Navier-Stokes system.
Right.
What happens when we try to move to the more realistic but also much more complicated 3D world? Does everything still hold true?
Yeah, that's a great question. Like, does the math still work out the same way?
Well, that's the million-dollar question, and unfortunately, there isn't a simple answer. While many of the basic ideas and techniques, they can be extended to 3D in principle.
Okay.
The actual mathematical analysis becomes way more complex, like orders of magnitude more difficult.
Oh, no. Why is that?
Well, for one thing, certain inequalities that are, like, essential for those 2D proofs, things like the Ladysenskaya inequality, they just don't have those nice direct counterparts in 3D.
So it's almost like the rules of the game change when we add that extra dimension.
Yeah.
The mathematical tools we use in 2D, they're just not powerful enough to handle the 3D case.
That's a good way to put it. And the Navier-Stokes equations themselves, they become much, much harder to deal with in 3D. Turbulence, that chaotic, unpredictable, swirling motion we often see in fluids, that really throws a wrench into things.
It's like going from a well-choreographed ballet to a mosh pit.
Exactly. Extending those results to 3D, it would most likely require developing a whole new arsenal of mathematical tools and insights. It's a really exciting area of research, one that's pushing the boundaries of our understanding of fluid dynamics.
It's pretty amazing to think that there are still so many mysteries to be unraveled, even in a field that's been studied for centuries.
I agree. And even if we just stick with the 2D case, there are still tons of open questions and avenues to explore. Remember, the authors made some very specific assumptions about those noise terms in their model.
Right, like how the noise was added and where it acted in the system.
Exactly. They assumed the noise was additive, meaning it was just added on top of the existing equations, and that it was acting on enough of those low modes to guarantee convergence. But what if we relax those assumptions? What if we allow for different types of randomness?
Yeah, like what if the noise was multiplicative, meaning its strength depended on the current state of the system? Or what if it didn't directly affect those low modes?
Those are great questions. If the noise were multiplicative, it would introduce a whole new level of complexity to the system. The dynamics could be completely different. We might see multiple invariant measures emerge, or maybe the system wouldn't even converge to any stable pattern at all.
It's like the noise itself could become this more powerful force, almost like a puppet master, influencing the system's fate in unpredictable ways.
Exactly. And if the noise didn't act directly on enough of those low modes, we might lose that crucial control mechanism that's driving convergence. The Foyas-Prodi estimate that we talked about earlier might not even apply anymore. The whole delicate balance of the system could be disrupted.
So it's a good reminder that those seemingly small details, those assumptions we make, they can actually have a huge impact on the overall behavior of the model.
Absolutely. Exploring those what-if scenarios where we tweak the noise structure and see what happens, that's a really fertile ground for future research. And it has implications that go way beyond fluid dynamics. It could help us understand complex systems in all sorts of fields.
Well, this deep dive has certainly been an eye-opener. I have a whole new level of appreciation for the power of mathematics to uncover hidden patterns in what seem like completely chaotic systems. And also have a whole bunch of new questions that I'm definitely going to be thinking about for a while.
Me too. It's been a truly stimulating exploration, and I hope our listeners out there are feeling just as inspired to keep digging deeper into these fascinating topics.
I second that. A huge thank you to everyone for joining us on this mathematical adventure. We hope you enjoyed it as much as we did.
And as always, don't forget to check out the show notes for links to the paper and other resources so you can continue your exploration.
Until next time, keep those minds curious and keep exploring the wonders of math and science. Okay, let's dive into a world where fluids mix, but a twist, a little bit of chaos thrown in. We're talking about stochastic systems today. You've given me a bunch of research papers about how fluids mix, like think oil and water. But the catch is there's this underlying randomness, always kind of shaking things up.
Exactly. It's like you're trying to predict the weather, but with like all these tiny invisible forces constantly stirring things up. And the concept we're going to be really looking at are invariant measures, which are basically like these statistical snapshots of the system. They tell us what we might expect to happen over time.
Okay, so why should anyone listening care about this? Why are these invariant measures so important?
Well, they're crucial for a whole bunch of stuff. Modeling real-world phenomena, like weather patterns, how financial markets work, even what's going on inside yourselves, all sorts of complex biological processes.
Wow, okay. So these papers, they focus on systems that are highly dissipative. What exactly does that mean?
Yeah, so that means they have a lot of internal friction. So it's kind of like imagine storing honey. Things tend to settle down eventually. But in these stochastic systems, there's always that randomness, that nudge pushing things around. So it's pretty tricky to figure out what happens in the long run.
So how do we even start modeling something like that? Like how do we model, let's say, oil and water, fluids that just don't want to mix?
Right. And the traditional way of modeling that is to think about like a sharp interface, a hard line between them. But that doesn't always work. So these papers use what's called a diffuse interface approach. It relies on something called an order parameter. It's denoted by phi, this Greek letter.
So instead of a hard line, are we talking about like a transition zone? Like where the oil and water kind of mingle a bit?
Exactly. So if phi equals 1, you're in a region that's mostly one of the fluids, like let's say oil. And when phi is -1, it's mostly the other fluid, so our water. And the interesting stuff happens when phi falls between -1 and 1. That's where the mixing really happens. That's our diffuse interface.
Okay, so it's like a gradient. It smoothly transitions from oil to water. But we're not just dealing with static mixtures, right?
Right.
These fluids are moving, and that's where I think the Allen-Cahn-Navier-Stokes system comes in.
You got it. So this system combines the Navier-Stokes equations for fluid flow and the Allen-Cahn equation, which describes phase separation. Basically, it captures both the movement of the fluids and how much they want to unmix.
So it's like this constant tug of war. The fluids are moving, but they're also trying to separate at the same time.
Yeah, exactly. And a key player here is the Korteweg force. This force models capillarity effects, which are basically the forces between molecules that create surface tension. Like how water beads up on a waxed surface, that's capillarity.
I see. Okay, so we've got the flow, we've got the separation. Now, the paper also introduces this logarithmic potential. It's given by the equation Thef sub log sub r Gandro. Thef to 1 plus r, ln 1 plus, ln 1 more, ln 1 more to ln r, sub 2-way sub ro1. So what does this represent? What's going on with this equation in our system?
Right. So this logarithmic potential, or F sub log sub, basically describes the energy landscape of the system. It tells us how much energy is associated with different configurations of the fluids, and it's all tied to these thermodynamic forces that drive the fluids to either mix or separate.
So it's like the fluids are constantly trying to find like the lowest energy arrangement. And this equation describes that energy landscape. And what about those decim sub-zero sub values?
Yeah, so those relate to the absolute and critical temperatures of our mixture. Basically, they tell us how easily these fluids mix. A higher HUP means they're more likely to mix, while a higher sub-zero sub, well, that pushes them to stay separate.
It's like adjusting the stickiness, I guess, between our oil and water.
Yeah, you could think of it that way. Yeah. But, we need to add one more ingredient to make things really interesting, to capture the complexity of real systems. The stochastic element.
Right, the chaos, the randomness.
Exactly. So in these papers, the randomness is introduced by adding these terms G sub 1 sub, DW sub 1 sub, and G sub 2 sub sub to our Allen-Cahn-Navier-Stokes system.
Those DW terms, those look intimidatingly mathematical. What are they?
So those represent cylindrical Wiener processes. It's basically a fancy way of saying we're adding random fluctuations to our equations.
It's like adding a random number generator to our system. So now we've got the flow, the separation, the thermodynamic forces, and randomness. How do we even begin to understand this?
That's where invariant measures come in. These are probability distributions that don't change over time, even with all the randomness. They're like a statistical snapshot telling us what the system is likely doing over very long periods.
So it's like we're finding a stable pattern amidst all the chaos. But how do we know they even exist in the first place?
That's a great question. And to answer that, these papers use some pretty sophisticated math, like the Krylov-Bogolyubov method, as well as the approach by Maslavsky and Seidler. These are tools that allow us to prove that these invariant measures actually exist.
Wow. So these methods are like guarantees that even in all this chaos, there are still some statistical patterns that will emerge over time.
Exactly. But wait, there's more. Remember, our system wants to settle down. It's highly dissipative. But the randomness is constantly stirring things up. So it's really hard to prove if there's only one invariant measure, a unique fingerprint for the system.
Right. It's like trying to find just one stable pattern, but the system's always being shaken around.
Precisely. So to deal with that, the researchers use a tool called Foyas-Prodi estimates.
Ah, Foyas-Prodi. Don't they focus on specific patterns in how the fluid flows?
Yeah, you got it. They let us analyze the long-term behavior by looking at a small number of low modes. It's basically like looking at the biggest waves in the ocean and ignoring all the little ripples.
I see. So we can understand the whole ocean by just focusing on those big waves. That's pretty cool.
Right. And these estimates are super helpful because they let us connect the behavior of those low modes to the entire system, even with all that randomness. However, to use them, we need to meet certain conditions.
Okay, what kind of conditions?
Well, it comes down to balancing several things. The viscosity, how much internal friction there is, the number of those active low modes, and a specific parameter from the Allen-Cahn equation. We need to make sure the system can settle down enough to counteract the random forces, and that those random forces are actually strong enough to affect those important low modes.
So it's all about finding that right balance, where everything is working together just right.
Exactly. And when that happens, we get something really amazing. The system reaches asymptotic stability. It means no matter where the system starts, it'll always settle into one unique and stable invariant measure.
So it doesn't matter how much we mix things up at the beginning, the fluids will always end up in that same pattern.
Yeah, pretty neat, right?
Yeah.
But remember, all this depends on one really important assumption. We need that randomness, the Wiener process, to be directly affecting those low modes. That ensures they're getting, properly stirred up.
Okay, that makes sense. Those big waves are really driving the whole system.
Exactly. And this idea is similar to a condition we often see with random systems, the non-degeneracy condition. Basically, we need the randomness to be rich enough to explore all the possibilities. Now, the papers also focus on systems with Dirichlet boundary conditions. This basically means we fix the order parameter at the edges of our fluid mixture, like pinning down the edges of our oil and water. It helps simplify the analysis.
So after all this analysis, what's the main takeaway? What have we learned about this chaotic system?
Well, the big news is that under the right conditions, when we have that balance between viscosity, low mode excitation, and those Dirichlet boundary conditions, this stochastic Allen-Cahn-Navier-Stokes system has a unique, stable, invariant measure. That means even with all the randomness, we can still predict and control how these fluids are going to mix in the long run.
Wow, that's huge, finding order in all that chaos. But we've really only scratched the surface here. There are so many mathematical details and techniques they use to get to these results.
Absolutely. We've laid the groundwork, and now we can really dive deep into the math behind it all.
All right, let's dig in. We've got the big picture, but how did they actually prove all of this? Like the existence, the uniqueness, the stability of these invariant measures. The math in these papers looks pretty intense.
Yeah, it definitely gets technical. So Let's start with the notation they use. They introduce these symbols, z-sub and z-sub. They represent the spaces of trajectories for, our order parameter, phi, and the velocity field, respectively.
Okay, so z-sub is like all the possible ways our oil and water could mix over time, and z-sub is like all the ways the fluids could flow, right?
Exactly. And then they use notations like C0TE, sub-sub-zo TE, and sub-zo TE, and super-sub-0 TE. These represent spaces of continuous functions, and they're really important for ensuring that the solutions to those Allen-Cahn-Navier-Stokes equations actually make sense, that they behave the way we expect them to mathematically.
So it's like all these function spaces are the mathematical scaffolding that keeps everything well-behaved, make sure the math doesn't go haywire.
Yeah, exactly. And then, of course, they have to make some assumptions about the system, about those parameters. For example, they assume that the potential function, F, remember that's the one governing those thermodynamic forces, well, it has to satisfy some specific properties.
Right, so we're putting some constraints on, like, the shape of that energy landscape, right?
Yeah.
Making sure the fluids don't just instantly mix or separate in unrealistic ways.
Exactly. And these assumptions, along with some conditions on the noise terms, G sub 1 sub and G sub 2 sub, well, they basically guarantee that the system will have solutions that make sense both mathematically and physically. It's all about setting the stage to actually explore those invariant measures.
Okay, the stage is set. So how do they actually prove that these invariant measures exist? What's the magic trick?
Well, they use some pretty powerful mathematical tools. One of them is called the Krylov-Bogoliubov method. It involves analyzing the long-term averages of the system's transition probabilities. Think of it like taking a long exposure photo of our chaotic fluid system. All the individual movements are blurred, but you start to see a stable pattern emerge.
Okay, I like that. So the invariant measure is like that stable pattern in the long exposure photo.
Exactly. And once they've shown that these measures exist, they start looking at their properties. One important property is the support. Basically, the support tells us which states of our system, which configurations of our fluid mixture are actually likely to be observed over time.
So it's like highlighting the regions where certain mixing ratios are more likely to occur over time.
Precisely. And they prove rigorously that the support of these invariant measures lies within a space where the velocity fields are smooth and the order parameter stays between let it 1 and 1. That's important because it means the solutions make physical sense, right? Our model is still grounded in reality.
Okay, so we've shown they exist, and they're physically realistic. But can we prove that there's only one? That there's a unique fingerprint for this system's long-term behavior?
That's the next challenge. It's all about uniqueness. Because if we can prove that there's only one invariant measure, then we know we're not dealing with multiple possible outcomes. Our predictions are going to be much stronger.
Right, it's like knowing that no matter how you shake that snow globe, the flakes will always settle in the same pattern.
Exactly. And to tackle this, they bring back those Foyest-Prodi estimates. Remember those. They help us focus on the system's low modes, those dominant patterns of motion.
Right, back to those big waves, the ones that tell the story of the whole ocean.
Exactly. And under certain conditions, like when the viscosity is high enough, the number of active low modes is large enough, and there's a specific parameter in the Allen-Cahn equation that meets certain criteria, well, they prove something really amazing.
Okay, I'm on the edge of my seat. What is it?
They prove that the system has a unique invariant measure. Only one. It's like bringing order to all of that chaos.
That's incredible. But wait, they don't stop there, right? They go on to discuss asymptotic stability.
You're right, they do. So asymptotic stability means that no matter what the initial conditions are, the system will always converge to that unique invariant measure. So it doesn't matter how you start things off, it always ends up in the same place.
So the system's fate is sealed.
Exactly. And to show this, they use a mathematical tool called the Wasserstein metric. It's a way to measure the distance between probability distributions. So they use it to prove that the system's probability distribution will always converge to the one described by that unique invariant measure.
So it's like watching how the mixing ratios change over time and proving that they always approach the same stable distribution, no matter where we started.
You got it. And their analysis actually shows that this convergence is exponential, meaning the system approaches its final state pretty quickly. It's a really neat demonstration of how mathematical tools can be used to understand these complex systems.
Okay, so we've covered a lot, but there are still so many details in these papers. Anything that stood out to you?
Oh, absolutely. Their analysis of the Foyest-Prodi estimates is just Really impressive. Remember, those estimates are key to proving both uniqueness and stability.
Yeah, they involve those low modes, right? But what's so special about their approach here?
Well, they actually derive these estimates in terms of expected values. So they're essentially averaging out the random fluctuations to get these deterministic bounds on how the system behaves. It's like filtering out the noise to see the underlying signal.
So we're taming the chaos, in a way.
Yeah, you could say that. And this lets them control the long-term behavior, even with all that randomness going on. The specific form of the Foyer's-Purdy estimates they get, well, it shows a really interesting interplay between the viscosity, the number of active low modes, and those important parameters from the Allen-Cahn equation.
Right. It all comes back to finding that perfect balance, doesn't it?
Yeah, it really does. And the papers also dive into the implications of those Dirichlet boundary conditions, remember? Those fixed values for the order parameter at the edges.
Yeah, like pinning down our oil and water mixture at the edges.
Exactly. And they point out that with these boundary conditions, those Foyer's-Purdy estimates take on a slightly different form. Basically, it reflects how those fixed boundaries affect the dynamics of the whole system.
So even those pinned edges can change how the fluids mix and flow.
Exactly. It's subtle, but it's important. It shows how carefully they've considered every little aspect of the system.
It's a reminder that those many details can make a big difference.
Absolutely. They've really done a thorough job analyzing everything. The boundary conditions, the viscosity, those low modes, the randomness, it all comes together to give us a really complete picture of how this system behaves over time.
It's really amazing how math can be used to untangle all of that complexity, finding order in the chaos.
It really is. And you know what? There's another fascinating aspect of this research that I think we should talk about. They use what are called coupling techniques to help prove that the invariant measure is unique. And this is where things get really interesting.
Coupling techniques? Yeah.
Oh, okay. Yeah.
Great. What are those? And how do they help prove that this invariant measure is really unique?
So coupling is a really neat way to think about stochastic systems. Imagine we have two separate versions of our fluid system, each starting with different initial conditions. Like maybe one starts with the fluids all mixed up and the other starts with them mostly separated.
Okay, so we have two oil and water mixtures, two different starting points, two different initial stirs.
Exactly. And what coupling does is it mathematically links these two systems together so that we can compare them directly. The idea is if we can show that these two systems, even though they started differently, end up in the same state, well, that's strong evidence that there's only one real long-term stable state, and that stable state would be our unique invariant measure.
Okay, I think I'm following. So we create these two parallel universes for our fluids, and we watch to see if they eventually synchronize. And if they do, it means there's only one possible ending no matter how things begin.
You got it. But it's not quite as simple as just letting them evolve randomly. We have to carefully link their randomness, those Wiener processes, in a way that encourages them to converge.
So we're not getting rid of the randomness, but we're sort of like manipulating it to nudge those systems toward each other.
Exactly. The paper uses a technique called generalized coupling. Instead of directly linking those Wiener processes, they actually introduce a shift in the Wiener process that's driving one of the coupled systems. And this shift is carefully designed to, subtly guide that system toward the other one.
Okay, so it's like we're giving one of those mixtures a little push, helping it catch up to its twin. But how do we know this shift isn't like artificially forcing the convergence? How do we make sure it's all mathematically sound?
That's an important point. And this is where that assumption about non-degeneracy comes in. Remember how we talked about needing the randomness to be rich enough? Well, this non-degeneracy assumption basically ensures that the Wiener process can explore the whole range of possible outcomes. It's like making sure the random stirring forces can reach every part of the mixture, preventing us from accidentally limiting what the system can do.
So we're letting things evolve naturally, but we're giving them a little help along the way. And those non-degeneracy conditions make sure we're not biasing the results.
Precisely. And the paper uses rigorous mathematical arguments to show that this approach, using this generalized coupling with the shift and the non-degeneracy assumption, well, it actually proves that the invariant measure is unique.
Wow. Okay, that's amazing. So we've dealt with the randomness and we've used this clever coupling trick to show that the invariant measure is unique. But what about those Dirichlet boundary conditions, the ones that fix the order parameter at the edges?
Ah, yes, you're right. Those boundary conditions add another layer of complexity. You see, they create this kind of anchoring effect that can really influence the system's behavior. It's like those fixed edges are subtly shaping the energy landscape, guiding the fluids towards certain mixing patterns.
So it's not just the random forces that matter. The boundaries play a role, too. How do we account for that in the coupling process?
Well, they show that with these Dirichlet conditions, we need to adjust the shift that we apply to the Wiener process. It's a small tweak, but it's important because it makes sure that the coupling still works properly, that it respects the constraints imposed by those boundaries.
So it's like we're fine-tuning those little nudges, making sure that neither system breaks the rules set by those fixed edges.
Exactly. It's a subtle point, but it shows how thorough the researchers are. They've thought about all the angles, all the little details.
This is amazing stuff. They've taken this really complex system, one that seems so chaotic and random, and they've found a way to understand it. They've uncovered this underlying order and predictability.
That's the power of math. It helps us see beyond the complexity and discover the hidden patterns that govern these systems. And, it's not just about abstract equations. These findings could have a real impact on how we understand the world. Think about how cells maintain their internal organization, or how ecosystems adapt to changes in their environment. There's so much potential here.
It's like we're seeing the world with new eyes. We can start to appreciate the order within the chaos. And it all comes from asking the right questions, diving deep, and really engaging with these challenging ideas.
Absolutely. And sometimes the most chaotic systems are the ones that hold the most beauty, the most wonder. It's all about looking for those hidden connections.
That's what makes these deep dives so rewarding. We get to go beyond the surface, explore the connections between ideas, and come away with a whole new perspective.
It's been a fascinating journey, and I can't wait to see where our next deep dive takes us. Thanks for joining me.
It's been a pleasure. Always happy to dive deep and explore these amazing ideas.